はい、
Good afternoon. Thank you very much for your participation in the annual Symposium 2024 on the ITER activities, a sustainable future opened up by fusion energy. My name is Yanagihara Kota, National Institute for Quantum Science and Technology, or QST. I work for QST, Naka Institute for Fusion Science and Technology, engaged in theoretical research of plasma wave physics. On behalf of the organizer, we'd like to invite Dr. Koyasu Shigeo, President of QST. He will be giving our opening remark. Good afternoon. My name is Koyasu Shigeo, President of National Institute for Quantum Science and Technology. Thank you very much for taking time out of your busy schedule to attend the annual Symposium 2024 on the ITER BA activities. The QST is engaged in R&D related to quantum technology, ranging from energy issues to healthcare. The focus of our event today, fusion energy, is one of such domains for which we spend many years. Annual symposiums on the ITER BA activities were hosted by Fusion Energy Forum of Japan, or FEFJ, but as part of a reorganization initiative, the QST has begun to host this symposium. The symposium this year is being held at the same time as the corporate exhibition and exchange session between the industry and the youth, hosted by the Japan Fusion Energy Council, or J-Fusion. I would like to express my deepest gratitude to J-Fusion for their cooperation. Now, in the Integrated Innovation Strategy 2024, the Japanese government states that Japan will aim to realize fusion energy as soon as possible by preparing a timetable that includes necessary national efforts toward achieving the first demonstration of power generation in the 2030s ahead of other countries. Based on that, the QST will further expedite initiatives to set up testing facilities and equipment on a practical scale, which can also be used by a startup, thus contributing to the sustainable future society and development of local communities. I'd like to briefly introduce R&D at the QST. 2 years ago, JT6TSA in Naka Fusion Institute achieved a plasma volume of 160 cubic meters, which was certified as world's largest tokamak by Guinness World Record last October. Also, we have developed a prototype of an outer vertical target of the diverter for ITER, as well as a gyrotron for generating high-power microwaves that can be applied to a demo reactor, showing steady progress. At present, we are reinforcing JT6TSA for heat testing and working on the plan so that we can start test next fiscal year while prioritizing safety over anything else. Rokkasho Institute for Fusion Energy has achieved an average beam power of 40 to 45 kW at 5 MeV in a demo test of LEPAC, a demo accelerator. This is the world's highest record as a radio frequency quadrupole accelerator in operation. Now we are assembling a superconductive radio frequency accelerator for acceleration testing at 9 MeV. Furthermore, to realize fusion energy power generation early, we are considering how we can further accelerate the demo reactor plan. The QST and Shinmutsu Ogawara signed a partnership agreement. We'd like to further promote industrialization on fusion technology alongside local communities. With regard to the ITER project, Dr. Pietro BARABASCHI, Director General ITER Organization, had sent us a video message thanking Japan for steady and great contributions to the ITER project and the construction progress according to the ITER Baseline 2024. We would like to share his message with you in a session later. I sincerely hope today's symposium will be fruitful and meaningful for the plans on the demo reactor as well as fusion energy power generation in Japan. Thank you very much.
President Kosugi, thank you very much. Next, out of busy schedules, we are joined by guest of honors and we'd like to invite them to give us remarks. And first of all, I would like to invite Mr. Nonaka Atsushi, State Minister of Education, Culture, Sports, Science and Technology. I am Nonaka, the State Minister of MEXT, and upon ITER PA Symposium, I would like to say a few words. And I have a cold, and I'm afraid I might not be very clear, but upon that remark, then LDP Energy Promotion Federation Chairperson Mr. Mori Eisuke and Dr. Sawa Takamichi and everyone at QST and diet members and those who are participating from industry and academia and everyone who are here, I would like to extend my deepest respect and gratitude for this opportunity. Recently, around the globe, climate change is becoming more serious, and for us to achieve carbon neutral, we have been doing everything. And to address this critical challenge, fusion energy has an extremely important role to play. And in major states, there are state strategies being put together and startups are born, and international competition is accelerating against this drop. April 2023, for the first time for us, Fusion Energy Innovation Strategy was put together. September last year, and Mr. Ishiba, who was the candidate for Prime Minister, he visited QST, Naka Fusion Institute, and about fusion power generation, development of and research and capacity building are important, and they claim the importance of this activity. And he also made a comment that the government needs to give more support in as next ITER program and BA activities, and to achieve demo reactor, laying the foundation and also promoting academia and research, and creative technology need to be born, and we were ready to provide the support. March last year, we worked with the cabinet and we established the fusion based on the state strategy. We have been taking actions again under the strategy and ITER program and BA activities to achieve fusion energy as soon as possible. They are playing extremely important roles in the ITER program or ITER project. And superconducting coils that Japan produced and devices produced by participating countries are being delivered, and those pieces are put together. July last year, toroidal field coil was delivered, and there was a commemoration to observe that opportunity. And Mr. Moriyama, who was the Minister of Education, participated. We were able to showcase our presence, and also many Japanese personnel working at ITER, and they are contributing to ITER project, and not only contributing ITER project but also for the capacity building for Japan. It is extremely important of our participation. And this year, for using ITER, we are prepare to reinforce our support to capacity development and also BA activities under the auspices of Japan and European government. Naka City in Ibaraki, the test devices JT60SA is now recognized as the largest tokamak devices in Guinness. And also Aomori Rokkasho and the fusion simulation research is being underway. And as a Ministry of Education, for fusion energy to come to fruition as soon as possible, we are committed to supporting ITER project and BA activities. And also the technologies or capacity that are being built, we are going to make the best of them and also work with the international community. And to that end, we will promote to laying foundation for demo reactor. Before I conclude, I will wish upon the productive symposium. Thank you very much. Thank you very much for your attention and congratulations on this occasion.
Thank you very much, Mr. Nonaka. Mr. Nonaka will have to leave the venue due to his political duties. Next, I would like to invite the chairperson of the League of Dive Members for Future Energy Promotion, member of the House of Representatives, Mr. Eisuke Mori, to take the floor. Thank you very much for your introduction. I'm the chairperson of the Liberal Democratic Party's League of Dive Members for Future Energy Promotion and member of the House of Representatives. I am pleased that this year's annual symposium is held and very honored to be able to participate in this event where all the people involved will meet together. The League of Dive Members for Fusion Energy Promotion of the LDP, I believe that it has been established in mid-1980s, so it means that it has been promoting its activities throughout the past 40 years. And I think that it was June 2006 when Karadash was chosen as the ITER site. Before that, the 3 years in advance to that, we used to have a fierce competition with each other in order to get appointed as the ITER site. Mr. Mori was the chairperson at that time. Even though we have competed fiercely for 3-4 years, Karadash has finally been chosen as the ITER site. However, because we made extensive efforts, the broad approach initiatives that will be taken jointly by Japan and Europe has been given as an opportunity for us. And as Mr. Nonaka has earlier explained, we have been able to accomplish a magnificent result. Currently, the ITER project is participating in an international project by 7 member states. And under the leadership of Director General BARABASCHI and Deputy Director Kamata, and with the support of many Japanese stakeholders, the project is making much progress. My understanding is that the structures of ITER has a high quality and highly functioning, and therefore it means that it is highly complex. The construction of ITER itself is a full series of R&D activities. That is my understanding. Amid this circumstance, Japan's technology is making contribution in the key components of the project. And I am very pleased and very proud of this achievement. On the other hand, the broader approach activities hosted by our country based on international cooperation between Japan and Europe, as well as the extensive support by the local community, is progressing smoothly in Rokusho Village, Omori Prefecture, and Nagasaki, Ibaraki Prefecture. And this has been touched upon by our Honorable Chairman as well as the Vice Minister. And what we have acquired knowledge and expertise by the broader approach, I believe that it will be reflected on the ITER project, which will lead to the early realization of the fusion energy. And we should focus our efforts on the development of the demo reactor, which is also a direction shown by the ITER project. We would like to continue developing our active efforts so as to support ITER. And at the Liberal Democratic Party, the project team has been established under the Policy Research Council. Finally, I would like to express my gratitude to all of you, the chairman, all the members of QST, who have worked hard to organize today's symposium. Thank you very much for your kind attention.
Mr. Mori, thank you very much. Next, we'd like to invite Mr. Izumisawa Seiji, Japan Business Federation Vice Chair, Chair of the Committee on Mutsu Ogawara Development, President and CEO of Mitsubishi Heavy Industries. I'm Izumisawa from Mitsubishi Heavy Industries and Chair of the Committee on Mutsu Ogawara Development. I'm in charge of promoting the Mutsu Ogawara Development Zone, where the QST Rokkasho Institute for Fusion Energy is located. First, I'd like to express my congratulations on this year's annual symposium on the ITER BA activities. Allow me to give a few remarks representing the business arena. As you're aware, against the backdrop of the tense situations in Ukraine and the Middle East, Japan is faced with energy crisis, which is the most significant since the oil crisis. To ensure affordable and stable supply of energy, to realize carbon neutrality, and to make our industry further competitive, it is essential to utilize nuclear power generation. While safety must be ensured as a prerequisite, we should restart existing power plants, develop and install innovative light water reactors, leverage nuclear power generation to the extent possible, and accelerate the development of future fusion energy. Japan Business Federation believes that we should regard fusion energy as a new industry, engage in steady R&D of the technology, and use it as a future energy source for Japan. From such a perspective, the Japan Business Federation has been requesting that higher priority be given to fusion energy in the next Energy Basic Plan. The draft Energy Basic Plan includes a statement that Japan will aim at putting fusion energy into practical and industrial use, as well as reinforcing R&D capabilities of the private and public sectors. Fusion energy does not involve the risk of depletion of fuel resources with intrinsic safety, where it automatically stops when fusion reaction is not sustained. It also offers an advantage of producing no high-level radioactive wastes. Practical use of fusion energy power generation will greatly contribute to solving global energy problems and taking measures against climate change. ITER, the International Project on Fusion Energy, has been progressing its construction work in a steady manner thanks to the efforts of all the people and parties involved. As mentioned, Japan has engaged in a toroidal field coil, which was produced and delivered according to the plan. Last August, I visited ITER and exchanged views with Director General BARABASCHI and people on the ground. I saw components and products delivered by companies in Japan and in each country being assembled, and was impressed by its sheer scale, recognizing the importance of the assembly work requiring great accuracy. There are many Japanese people playing a major role in such a scene of international cooperation. Many engineers and researchers. I found it reassuring to see the motivation and effort of the people on the ground supporting the activities. As the schedule has been revisited, it is vital to address various challenges in a steady, step-by-step manner to make progress. I hope the DD fusion operation will be achieved in 2035 to make the technology further mature so that this will subsequently lead to the DT fusion. BA activities by Japan and Europe have shown progress in studies to establish technical foundation necessary for the demo reactor, as mentioned earlier. In October 2023, Japan's JT60SA achieved the first plasma, and in September 2024, the world's largest volume of plasma was certified as a Guinness World Record. This is a significant step forward to the practical use of fusion energy, as mentioned. Based on this, I have high hopes for the demo reactor to be further specified early in Japan. Furthermore, bases for BA activities such as Rokasho Institute for Fusion Energy and Naka Institute for Fusion Science and Technology are where we can develop younger researchers worldwide. I firmly believe the government should set up a good environment so that younger generations can engage in such activities with hope and in a continuous manner. Looking at each country's activities in parallel with ITER, we can see international competitions are accelerating toward industrialization by offering large-scale support. Fusion power generation rapidly attracts much attention and high expectations with large-scale investment made in startups. Japan set a fusion energy innovation strategy and according to it, found Japan Fusion Energy Council in March 2024. In Japan, we have high expectations for startups derived from R&D in fusion energy. With the emergence of markets from the technology and surrounding ones, I expect Japanese companies and industries can lead the development of fusion energy based on the activities of Japan Fusion Energy Council. Lastly, fusion energy development should not be just a fad. It requires continuous and steady effort. Therefore, I sincerely hope this symposium will be a great opportunity to further promote such activities by those engaged in this field. And with that, I'd like to conclude my remarks. Thank you very much.
Thank you very much, Mr. Izumisawa. Next, I would like to invite Mr. Hyodo Masayuki, trustee of Keizaido Yukai, chairperson of Energy Committee, chairman of the Board of Directors of Sumitomo Corporation. Thank you very much for your introduction. I am Hyodo, trustee of Keizaido Yukai and chairperson of Energy Committee. And first of all, I would like to congratulate on this occasion to have the annual Symposium 2024 on the ITER project and BA activities, and those who are engaged in the fusion energy from public and private sectors and academia. And I feel very honored to be able to address you. And globally, demand of energy is growing, and we have also climate change is becoming more serious, and application of fusion energy, expectation for fusion energy is becoming ever more great in business. And since 2023, I have been serving as energy chairperson of Energy Committee at Keizaido Yukai, and since last year until this year, and we have put together a proposition of to utilize nuclear power, and we also made some propositions to the seventh energy basic plan. And in the process of making our proposals, and I feel that momentum for fusion energy is becoming ever greater, and also the member companies are very aware of the importance of fusion energy, and we believe it is important to keep this momentum going. And last year, those who are from industry and the private sectors, thanks to your tireless effort, ITER tokamak building was finished, and Japanese companies are participating in building the demo reactor. They are providing important parts, and we saw a significant progress in ITER project and BA activities. And last year, I personally visited ITER, and together with Mr. Izumizawa, who just made remarks before me, and not only the large Japanese corporations, but also small and medium companies in Japan participated in putting that plan together. And I was explained that how the Japanese companies have been conducive to this effort, and I was very touched by that personally, and I vividly remember as if it happened yesterday. In the fusion energy, and Japanese companies are making such a great contribution, and also, and to October 2023, the first plasma was achieved, JT60SA, and the largest tokamak was certified as a Guinness. And that was a great news, and I was very happy to hear that. And the government of Japan has an innovation promotion strategy in 2024 by 2023 to achieve power generation of fusion. There is a lot of positive news in the field of fusion last year. And if you look at what's happening globally, last year, November, in Rome, Italy, we had a World Fusion Energy Group, and I participated in a meeting to celebrate the establishment of the group. And at the meeting, from all over the world, fusion people who are in the fusion energy field come together and to share the current status and public and private partnership, and about creating business. We had such animated discussions, and I personally participated in a meeting, and through that experience, the fusion energy to be applied, I feel that there are competition and co-creation. So the competition and co-creation, I feel that they are happening in a full-fledged manner. I personally had that experience in Japan, and public and private and academia, we all need to work together to make realize commercial reactor and integrated fusion into the energy mix in the future. We need to share a long-term vision, and we need to involve important stakeholders in and outside of Japan. It's important also to build a capacity. And to this end, in March last year, Fusion Energy Council, J-Fusion, was established. And our company participated in creating that organization. And one of our colleagues is serving as a vice chairman. And under the auspice of J-Fusion, academia and industry will all come together to accelerate this endeavor and to create breakthrough of technology, and also to achieve power generation fusion. We need to develop capacity to be able to achieve integrator, and also to make fusion energy a reality. We need over generations. We need to put intellect of industry beyond a generation, and we need to build that intellect to be able to hand over technology. And QSD, since 2 years ago, QSD has been operating so-called open innovation integration window, and that is a part of their action or effort to build capacity. And we need to go over the borders of academia and industry to be able to achieve fusion energy, and we all need to work together to be able to achieve that. And with this standpoint, this symposium is extremely important. I hope that your active discussion will ignite plasma and the fusion amongst the different fields will expand. And thank you very much for your attention.
Thank you very much, Mr. Hyodo. In addition to our guests who are just greeted us, there are many other guests here in this hall, so I would like to introduce them to you. I would like to introduce the guests starting from the left and moving to the right, seeing from the audience to the stage. Mr. Suzuki Yoshihiro, a member of the House of Representatives. Thank you very much. Mr. Suramoto Seiki, member of the House of Representatives. Thank you. Mr. Yamazaki Makoto, member of the House of Representatives. Thank you very much. Ms. Nagaoka Keiko, a member of the House of Representatives. Thank you very much. Mr. Akaike Masaki, a member of the House of Councillors. Thank you very much. Mr. Katsume Yasushi, the member of House of Representatives, his secretary is in attendance on behalf. Mr. Asano Satoshi, a member of the House of Representatives, his secretary is in attendance in this place. Thank you very much. Ms. Okano Junko, the member of House of Representatives, her secretary is in attendance in her place. Thank you very much. Mayor of Naka City, Ibarra Prefecture, Masaki Hikaru. Thank you very much. And also, we have received many congratulatory telegrams for today's symposium, so I would like to only introduce the names due to time constraints. Mr. Tanahashi Yasumi, member of the House of Representatives. Mr. Morimoto Shinji, who is the Secretary General of the League of Members from Future Energy Promotion. Thank you very much.
Let us move to the keynote speech. First, we would like to invite Mr. Baba Daisuke, Director, International Nuclear and Fusion Energy, Affairs Division, Research and Development Bureau, Ministry of Education, Culture, Sports, Science and Technology, and Cabinet Office. He will be talking about fusion energy innovation strategy. Mr. Baba, the floor is yours. Good afternoon. I'm in charge of fusion energy in MEXT and Cabinet Office. My name is Baba. Today, from the government perspective, I'd like to talk about our initiatives on fusion energy, as well as I'd like to touch on the trends, overseas situations, as well as our activities based on the national strategy. As mentioned in the opening remarks, 2 years ago, April, Japan issued Fusion Energy Innovation Strategy, a national strategy on fusion energy. And this has been based on the trend of overseas countries, and we will be pursuing various activities and initiatives. In the past, MEXT has focused on R&D, but not only that, we'd like to aim at industrialization, and for that to be achieved, we'd like to promote the various activities and initiatives going forward. That's what this strategy had set about. And this national strategy, the 2 years from now, we will be revising the strategy in the near future. And as mentioned, in overseas countries, they are trying to set up national strategy with a great momentum. I hope the screen is shared now. One moment, please. I'm now trying to share the screen. Well, let me move forward. As I've been in charge of policies in the recent 1 and 2 years, we saw a great changes in the situation represented by the ITER and BA activities, relationship with European countries, as well as the cooperation with 7 countries, and as well as G7 mentioned by Mr. Hyoto, through the initiative of Japan. For the first time in history, the G7 outcome documents included the fusion and the document. In Italy, World Fusion Energy Forum, the ministerial meeting is held. So there's an activity based on the international collaboration and cooperation, but at the same time, the competition has become fiercer as a result. I hope people joining online can now see the screen. This is the situation in each country, starting with the United States. In the US, although they have the federal government, but they set up a national strategy 2024 related to fusion energy. And in the UK, they set up the strategy in 2021 and revised it in 2023. And in Germany, last year, they set up the national strategy aiming at 2040. And in China, I visited the country, and they have started building the large-scale testing facilities group, CRAFT. And also, with regard to ITER, there has been the proposal on the baseline update. There are various activities in progress at the same time. G7 in June 2024 and G7 summit in Italy, they included the term fusion in the document. G7 summit members announced that they have the recognition that fusion can offer the permanent solution to climate change as well as energy security. And that is the view not only in Japan but shared with various countries. In G7, the G7 World Fusion Working Group as well as World Fusion Energy Group were decided to be established. In November, in addition to Mr. Hyoto and the Director General BARABASCHI, the Chairman Konishi of J-Fusion, and on behalf of the government, the State Minister, next State Minister has participated in a discussion with each other in this conference. And November 4th, a G7 Working Group on Fusion Energy has held for the first time, and the Cabinet Office Deputy Director General has joined this meeting. We are seeing various activities in progress in this domain. While on the other hand, we are seeing fierce competition at the same time. This is the activity we have seen in the recent 2 months. At the top, what is called the largest startup in this field is CFS, so Commonwealth Fusion Systems. They announced that they will build or a site in the state of Virginia, the US, to create fusion energy, a commercial power station. They've selected out of more than 100 places, spending 2 years collaborating with the state government. And also from the local utility company, they acquired the land. They are trying to conduct activities. And in the UK, the administration has changed, as you're aware, and under the new administration, they announced that they will be spending £410 million in this area through the talent development and setup of facilities. They will be supporting the rapid development of this technology, announced very recently. And what we should be mindful is that the demo reactor step will be set up by 2040, and they've already started the selection process of the operators. And also the coal power station, and they are trying to use the land to reuse the land for creating power station so that they can add new jobs. And in China, as mentioned, they built what is called CRAFT, and also East, the tokamak experiment systems achieved more than 1,000 seconds containment of plasma. Therefore, they showed a great progress in terms of fusion energy power generation. We are seeing these activities in progress at the same time. Under such circumstances, 2 years ago, April, we set the national strategy on fusion energy. We'd like to regard fusion energy as a new industry. We would like to enter this competition of supply chain and being established. We don't want to miss this opportunity and seize this timing. And also, we'd like to take a multifaceted approach, including industrialization, including ITER plan and BAA activities and demo reactor development. And we'd like to set up industry associations, support R&D of startups, and have discussion on safety and support of the new technologies. And fusion energy offers the possibility as a solution to energy and environmental problem, but at the same time, not just makes but the cabinet office and collaborating with various governmental offices and agencies we are now working on. One characteristics I'd like to touch on is that these three pillars composing the strategy. The first one is the strategy to develop the fusion industry. As mentioned, J-Fusion has been decided to set up. That was April 2 years ago. On top of that, the safety and standardization and like-minded countries started discussion. And as you may have heard in the mass media, the report, the safety, the framework needs to be set up. And at the moment, the cabinet office had started discussion on that. Of course, technology has been one of the pillars. Through ITER and BA activities, we'd like to acquire core technologies, and we can hear a lot of results and outcomes on this. But the technology we developed through ITER and BA, how we can make use of the technology, that is one of very important missions we'd like to address. And promotion, including QST, and the laser research lab in the University of Osaka. We'd like to make good use of these organization and promotion structure so that we can scale this activity both privately and publicly. And we are now engaged in various activities in this domain. And another thing I'd like to touch on, the talent of human and the talent development is something I'd like to touch on later. And I'd like to move to the recent initiatives based on the national strategy. The first pillar, J-Fusion, has been set up accordingly. And SBIR, this is the support for startups, and to enrich the support at the moment, we have been supporting 4 startups through this program. And CSTI, through this conference or meeting, we decided to regard fusion as the 10th moonshot target. Other targets are related to healthcare or environment. In addition to this, we've added fusion as one of the targets. And this is a great message that we can emphasize, that we can involve so many people. And I think many participants have joined. JT60SA, the first plasma, was celebrated in Naka. The 2 ministers, as well as the Commissioner Simpson, has joined, and this was a great milestone for us. And also the promotion structure. Centering around QST, we'd like to establish the structure where academia and private companies can join, as well as offering training programs, especially with regard to ITER and JT60SA. We have been engaged in talent development utilizing these. And I discussed this last year as well, but as you can see, as a future policy, we'd like to make good use of international collaboration to set the foundation necessary for demo reactor, and then collaborate with an industry association and set up the basic framework or way of thinking about how we can ensure safety. And as the government, we are accelerating these activities. In ITER BA, we have been spending many years in Japan's R&D locate this activity like this, in this manner. And JT60 is one of the 3 largest tokamak, and we've updated SD super advanced as superconducting systems. That is one of the message we have conducted in this activity. And ITER has been engaged in by 6 countries across the globe, and the University of Osaka, the labs, and in the Kyushu University and Tsukuba University. There are various systems and equipment we have in Japan. And according to a survey by IAEA, the fusion facilities, Japan ranks the second in terms of this, the number and the scale of these facilities next to the US. We'd like to make good use of these assets we have in Japan. At the same time, we'd like to offer support to startups. We'd like to do backcasting from the future, the image of the society, and by integrating this, we'd like to make the next step forward. ITER will be further detailed in the sessions later, but as mentioned in the opening remark, the toroidal field coil, the ceremony, I'd like to touch on the message around the time. The former MEX Minister Murayama has touched on this. This offers the high accuracy in containment plasma, and it requires a lot of development of technology, and it clearly shows that monozukuri manufacturing capabilities of Japan has been fully exercised leading to the completion of toroidal field coil, overcoming various technologies. And also, based on the baseline update, we are seeing steady progress of the ITER plan. That is something we'd like to emphasize. When we see news only, there are various opinions, but I would very much encourage you to take a look at this actual construction site on the ground. There are so many people participating in this initiative, trying to achieve the same goal, going beyond national borders and generations. That is something you can see. So if you're interested, please let us know. We would very much like to offer such opportunities to you if you are interested. While at the same time, broader approach activities. Japan and Europe have been doing this based on an agreement with 3 pillars. We have 2 committees every year. In December, the steering committee was held in Belgium. There was the report that the progress has been made, and Aomori Rokasho has been supporting this activity to a great extent, and also support from the European countries and organizations have been expressed together with the participants. And next steering committee will be next April in Naka, Ibaraki Prefecture. The members will be gathering in Naka next April. When we take a look at this activity, various countries and Japan as well as from Europe, we are having a discussion going beyond national borders, engage in trying to achieve one goal. I think it's one of the symbols showing the milestone of science and technology, and I think that has been emphasized in the plasma and the plan we've been engaged in. We'd like to generate further outcomes, and we'd like to be engaged in talent development based on the insight and outcome we've obtained through this activity. Last November, Director General BARABASCHI has visited and made a courtesy call to MEX Minister Abe. In exchanging view exchanges, Director General BARABASCHI explained the progress of ITER plan, and MEX Minister Abe expressed gratitude and respect about the steady progress of assembly and installation under the leadership of Director General BARABASCHI. And they were on the same page that many Japanese staff members can play a major role in the ITER organization. That would be important from the perspective of contribution to the plan as well as the talent development of Japan. As mentioned earlier, the MEXT would like to collaborate with domestic universities as well as J-Fusion and the Ministry of Foreign Affairs so that we can further increase the number of Japanese staff members working for the ITER organization. This is what we have in mind in MEXT, the direction we'd like to be heading. Last June, we made a cabinet decision, and it specifies this concept. and the people engaged in demo reactor development to nurture and develop talent in a strategic manner. We'd like to create a comprehensive training system through the inter-university cooperation. To realize this in the next fiscal year, we are now having concrete discussions, and through the collaboration, the UK, the US, and Canada, we'd like to enforce the collaboration with these countries as well as the ITER organization so that we can enable the talent development in this domain. And specific activities, ITER International School, IFS, and the Fusion Science School, or JT68 International Fusion School, JIFS. ITER International School has been conducted between ITER organization and 7 countries. Last year it was in Japan, next year in India and France. And last October, Nagoya hosted this activity for the 2nd time in Japan. In holding this event, we were concerned how many people will be joining the event, but it turned out that the participants are 100 from Japan and 100 from overseas countries. So 200 people in total have joined in the training session, receiving the same lecture, engaged in the same research. It was actually sad because there were more participants wanting to join the event. And next year, that would be in France, but only the students and younger researchers had to apply themselves. But from the next fiscal year onwards, we would like to we'd like to offer these activities and receive application from the people or students across Japan, so that we can offer some monetary support in the transportation and things as well, and so that they can build a better collaboration and improve their skills through the relationship and this opportunity. And International Fusion School, based on the joint statement, we will be reinforcing this activity. And last year we had a 2nd session, and as Mayor Obnaka was present at the time, 10 people from Japan, 10 people from Europe, the younger researchers joined this session, spending 3 weeks or 4 weeks in a summer school format. In the 2nd event and onwards, Japanese participants have visited ITER themselves. Therefore, we are trying to make this event more attractive to the participants. The Japanese government would like to continuously conduct this activity going forward. And as a student joining online, at the end of February and March, ITER has been accepting the internship. In the past, the accommodation fees were the money you can only receive in terms of ITER internship. But if you're selected for the internship, we'd like to support transportation as well as accommodation fees during the ITER internship, so that you can. We'd like to provide more support to the motivated students in this regard. For the specific information, we'd like to give an announcement, so please check that out. Lastly, early realization and industrialization of fusion energy. As briefly mentioned, Prime Minister Ishiba, when he was one of the candidates of the head of LDP, he has visited a paid visit to JT60A. The JT60SA, and I may be repeating myself, but Prime Minister Ishiba emphasized the importance of supporting research in this domain from various perspectives. He said that he'd like to provide a support as necessary, otherwise we would not be able to early realization of fusion energy use ahead of other countries. And last week he emphasized the Japan with delight as phrased emphasized by mass media, but he clearly talked about fusion energy as well, as he said that he'd like to promote a science, technology, innovation basic plan and facilitate investment in strategic areas including AI, quantum, bio, space, as well as fusion. Of course, this would not be achieved by government alone. all the participants joining the symposium from the industry, academia, as well as the members from the overseas embassies, especially students. For the next generation, we would like to pursue activities based on your understanding. We would very much appreciate your continuous attention in the later session as well, and would like to cooperate together to realize this concept. Thank you very much.
Mr. Baba, thank you very much. Now I would like to introduce Mr. Ogata, Rintaro Ogata, a member of House of Representatives. And next, from QST Office of Fusion Energy Promotion Strategy, I would like to invite Mr. Oyama Naoyuki to talk to you about his project. Thank you very much for your introduction. I am Oyama from Office of Fusion Energy Promotion Strategy at QST, and I'm here to talk to you about ITER project and JT60SA test operation to make an early realization of a demo reactor. At QST, and this is a roadmap created by Fusion Science Technology Committee, and following that roadmap, we are doing our research activity. And you have years, and it's 2025, and number 4 is the demo reactor development. We are at conceptual design, and we are at developing elemental technologies. And this is where we are at QST. And the committee made a plan, which is to promote fusion demo reactor promotion. And we are working on the conceptual basic concept for demo reactor, and using the ITER project and BA activities, using all the capacity and technologies. And this is all hands on deck to create concept. And we are also creating elemental technologies. And for conceptual design, we have some members coming from universities and industry, and we have a joint team to build a demo reactor. And 1.5 minimum kilowatt, which is 3 times larger than ITER, using that fusion output, we generated 640,000 kilowatt, and we supply 250 kilowatt into the electricity system, and that's what we believe what we can achieve. As you can see on this slide, this is the conceptual design of tokamak type. And for conditions for designing, and major devices are toroidal field coil, breathing blanket, and diverter. We design them based on the ITER technology, and the technologies that ITER does not have. We have power generation plant technology and test operation experience, and we also adapt new ideas coming from university. And reactor core and plasma, we have ITER based on. We design based on the result to be generated by ITER and JT60SA. And what this is the conceptual design, power output and utilization rate, and self-sufficiency of fuel. And those are the targets for demo reactor. And to build a demo reactor, we are laying the foundation, and we're using that related businesses to lay the foundation, and we are working on the conceptual design and developing elemental technologies. And at QST, we have ITER project BA activities to maximize the achievement. We are using those results to maximize, and then use that to demo reactor. But we need to do more to build a demo reactor. We need more than what we have achieved under ITER project and BA activities. If you look back, before ITER project was born, we had an activity of engineering design activity before ITER came into force. We have a solenoid motor coil diverter, remote operation diverter cassette and toroidal motor coil, and a vacuum container sector, blanket distance operation, and blanket module. And those are the large engineering research and development that we performed. Based on this experience, when ITER project was born, Japan was able to provide or supply critical devices. And today, ITER acquiring ITER, those ITER devices are being put together, and to build demo reactor, there are still so many gaps between ITER and demo reactor, and to fill in those gaps, we need demo reactor engineering phase design and enabling technology need to be developed in a certain phase. And when it comes to fusion energy innovation strategy, states industrialization, that needs to be considered to fill the gap between the technological gap between ITER and demo reactor. If we are able to fill the gaps, that will help us to realize or make our realization. And to that end, we need to accelerate research and development in engineering, designing, and developing enable technologies. By accelerating, we have ITER plan and BA activities that we have capacity and experience, and we need to integrate all of that to accelerate the project. And to build demo reactor, we need facilities, and that is summarized in the action plan, but we build experience through ITER plan and BA activities, and also we need to consider what we have inside and outside of Japan facilities and Low-Casho Fusion Institute and Low-Casho Fusion Institute. They need to lay the foundation to be able to build demo reactor. I will not go into the details, but as you can see a diagram left bottom, those are facilities, Naka Fusion Institute. And on the right-hand side, those facilities to be built at Low-Casho Fusion, we need both. And those facilities are not to serve only research development at QSD, but for fusion energy startups and industries and the university institute. And I'm sure that those facilities will be conducive to research and development performed by universities and other institutes. And to lay the foundation for demo reactor, we have already started something which is a fuel system safe test site. And QSD has performed a fuel system research and development. We have subsystems such as high-density tritium processing system and fuel pellet production technology. However, we do not have experience in those fields. And for proceed with research and development, we need test different technologies. It's inevitable for us to test different technologies, but we don't have any test site that can encompass all the different technologies. And also for legislature for demo reactor, we need to build up technologies to be able to handle fusion fuel. To that end, we need this kind of a system of facilities, and we have built the facilities we need to build the facilities at Low-Casho Fusion Energy to be able to test fuel cycle. And to apply fusion energy, we have an international cooperation, which is ITER plan, but also on top of that, there are research and development plans being implemented by different countries, which was mentioned by Mr. Baba earlier. Just to give you an example, ITER engineering R&D, China was not participating, but they built a craft. It's a large test site, and the craft and the operation of craft, and also test device best, which is as big as JT60SA, and to acquire fusion element elementary technologies, they have already started large test operation. Against this backdrop, we need to work with the international community. But however, to be competitive, it's also extremely important to have test sites within the borders of Japan. And Mr. Baba also mentioned in his presentation, we need to also pay attention what is going on in and outside of Japan and at QST to be able to realize power generation as early as possible. We started considering if that ITER size demo reactor will make sense, and this is the roadmap. And axis is the years, and to achieve demo reactor. And by 2020, we'll continue this phase by 2025, and then make a decision whether we can make a proceed to a demo reactor. If we wanted to accelerate between ITER and demo reactor, there are gaps to be filled. And according to the roadmap, starting operation, and we have target from 1 to 3 on the left-hand side, and several thousand of kilowatt need to be achieved, and also self-sufficiency of fuel. Those targets need to be achieved at the same time. But to 0.1 gigawatt class to generate, the first target is to generate 0.1 gigawatt class. And so that's the first target. And if we started considering if we can front load this target. And so this is what we are currently working on this page. First, we need to upgrade major devices to improve the quality and performance of devices. And first phase is to focus on to implement blanket for generation and to generate the ITER size plasma. And for the plasma, in a short pulse, by operating plasma in a few minutes, the net electricity should be 0. And on the right-hand side is diagram. I like to add ITER size. When I say ITER size, it's indicated blue is the toroidal field coil. This should be same as ITER size. So that's our assumption. And in a dotted line, ITER size plasma should be achieved, and the dotted line and blue, that's a gap where we are planning to implement blanket for power generation. And the second, on top of generation, we need function blanket to breed fuel by using that blanket. From the solid line and dotted line, plasma will be smaller, but a few hours in a long pulse, we should be able to manage plasmas and to test breeding fuel. So that's the second phase. And the third phase is that heat and using high to make a device to generate current and heat at a high efficiency level. And at the constant operation, we will test if we can generate 100 megawatt of electricity. So we would like to take a phased approach to upgrade devices. And is it technologically possible or not? That's what we are studying at QST. And to build a demo reactor, there are safety regulations and standards that need to be formulated. At QST, we use Agile Nations framework about safety regulation, and we provide our advice as an expert, and we're also providing technological support. And we put proposal together. We participated in putting the proposal together at also cabinet. There's a Fusion Energy Strategic Committee, and below that we have Fusion Task Force. And QST, we sent some committee members from QST, and we also provided some information and about building standards, Atomic Energy of Society of Japan, and the Japan Society of Mechanical Engineering, and Japan Society of Main Technology. We have a communication with those committees. And the bridge QST was designed as bridge program. So when it comes to building a framework of international standards, and we are also participating in developing young talent and also collecting necessary data. By 2030, we would like to build an international standard before 2030 to build a supply chain. And I've been talking about early realization of a demo reactor. Those are the actions we have been taking, but we will appreciate your support and consideration and collaboration. Thank you very much.
Thank you very much. Now I would like to introduce the guests who have just arrived. Member of the House of Representatives, Mr. Shuji Ikuhira. Thank you very much. Now let's move on to the next presentation. Mr. Ide Shinsuke, Deputy Director General, Naka Institute for Fusion Science and Technology, under the title of Progress of ITER Project and the Status of JT60 Essay Towards Heating Experiment. The floor is yours. Thank you very much for your introduction. I am Ide from Naka Institute for Fusion Science and Technology. I would like to report on the progress of the ITER project and the status of JT60 essay towards plasma heating experiments, specifically, and what we have been doing. As Councillor Baba has earlier mentioned, the scientific feasibility results demonstrated around the world, especially at JT60 at Naka Institute, we were able to get the equivalent energy multiplication factor exceeding 1, which means that fusion was able to generate a power that had been input. And also, we were able to demonstrate that the airborne temperature exceeded 500 million degrees Celsius. In response to this result, we are now focusing on demonstrating a fusion burning demonstration, and based on international cooperation, construction of ITER is now underway. At QSA, through procurement of the components of JT60 SA, QSA is still working with universities, research institutes, and industry in Japan and abroad to the success of ITER and the demonstration of power generation, the demo reactor. Firstly, about the ITER project, maybe I might be overlapping from the earlier presentation. It uses deuterium, tritium, so to say, real fuel to demonstrate sustained fusion burning, and that is the objective. Therefore, Japan, Europe, United States, Russia, India, China, and Korea work together. And we have a huge device at southern France, which is 30 meters in both length and width. And first of all, because we have a message from Dr. Pietro BARABASCHI, DG of ITER organization, please look at the array.
I'm very sorry that today I cannot be with you in person for this important annual symposium on ITER and the broader approach. But it is my great pleasure to offer a short message to you today. First of all, I would like to thank you for the steady and substantial contribution which Japan gives to the ITER project. This has been very critical for the project success in terms of fabrication and on-time delivery of key ITER components, and to enrich the project with your knowledge and expertise. Continued reliable contribution from Japan, and just like from all ITER members, will remain very important to keep the ITER project moving in the right direction and on schedule. 1 year ago, at the time of your last symposium, ITER was facing a very challenging time. We were in the middle of repairs of key components. We were working to improve ITER's quality culture, and in parallel, we were preparing a new baseline to present to the ITER Council. This year, I'm pleased to present you with a more positive picture. In fact, I would say very good news on the ITER progress. We proposed a new baseline of the project to the ITER Council meeting in June. And based on the analysis carried so far by the ITER members, the Council in November has endorsed the overall baseline approach that we presented. So with this baseline 2024, we are now focusing on delivering value as rapidly as possible. This means driving towards the start of research operation with a machine that has most of the substantial components installed, in particular including the divertor, so enabling practical and substantial plasma operation that will lead all the way to full plasma current as soon as possible. In parallel, it's important to note that we have established a constructive mutual understanding with the French safety regulator regarding the stage licensing approach in the new baseline. So I am very proud to report that in addition to these supplementary activities, such as the baseline and the project organization, 2024 was actually the best year ever in terms of productivity achieved at ITER. The construction project, supported by all parts of IO and the DAs, delivered more than 100% of what was planned the year before. And we did so on cost and on time. So there is a little bit too much detail to report everything, but I would note that the repairs of the thermal shield and vacuum vessel sector are ongoing as scheduled, and the first sector modules are now being assembled and will soon be put inside the pit. The last vacuum vessel sector has arrived from Korea, as well as the first sector from the EU. This gives us confidence that the remaining vacuum vessel sector should arrive on schedule in the new baseline. In July, we celebrated the delivery of all toroidal field coils, 9 coils from Japan and 10 from EU, in the presence of the Minister of MEXT, and this was a very important achievement. We now also have all colloidal field coils and most of the central solenoid on site, and the RF building is completed, and we have started the installation now of 8 gyrotrons delivered from Japan. And there is really much more, but I believe this is enough to validate my earlier statement regarding the substantial nature of Japan's contributions to ITER. I would also like to highlight Japan's contribution to our revision of the ITER research plan. So on behalf of all the ITER organization and all the members, thank you. I wish you an excellent symposium, and thank you for your attention.
はい、それではです。
So based on the material that I have received from the ITER organization, I would like to make a report on what they have doing. This is an aerial view of the site. As of last June, the building was 85% complete, and the site that supplies system that supplies power to the site is already and stable, as well as the site's cooling system. As DG BARABASCHI has just mentioned, the toroidal coils, the most important component, have been delivered, and celebration ceremony was held last year. I believe that this is an epoch-making event. And also, the toroidal field coils, which control the position and shape of plasma, was also completed in 2024. I believe that this was another milestone. The power supply to these coils has also been completed, and the world's largest helium refrigeration plant to cool the superconducting coils is now in operation. Start of the production of liquid helium is another major achievement. As for the diverter, the most important component in the vacuum vessel, we were able to complete a Japan-made prototype, which I will touch upon later, and this is another big achievement. One of the major concerns that repairs at the vacuum vessel sector have been completed, and assembling has begun. In the spring this year, the vacuum vessel sector will be integrated with the Japan-made toroidal coils and then be returned to the tokamak bed. Like this, the work on the side is progressing quite smoothly. As Director General BARABASCHI has said, throughout 2024, the ITER project has executed its plans at the highest rate ever than any other year. ITER organization has made a new baseline and starting operation with many components, including the diverting from the beginning of the plaza operation. This is the basic content, and the ITER Council have held last November had endorsed the new baseline's overall approach. This means that the start deuterium operation will start as initially planned. And now I would like to move on to Japan's contribution to the ITER project. We are in charge of procuring various devices. The large ones is the most important, toroidal field coil. Among the 19 units, 9 of them is our task to deliver. And underneath, there is the diverter, which is underneath the vacuum vessels. And there are 58 such devices lined up around the bottom of the vacuum vessels. And the outer target is what we are in charge of, and also in addition to that, the heating system and diagnostics and so on are what we are in charge of, but I would like to focus on several of them in today's report. First, starting from the diverter. And we are in charge of the outer vertical target, or in short, OVT. And it is 1.3 meters long, and the prototype has been completed, and after passing the performance test, was delivered to the ITER site, and this photo shows that moment. And a response to this prototype completion and the first production line, production of the actual prototype has started. And because we'll have to produce 58 units, we are now working to establish the second line, and the prototype for this is now being worked on. This is the heating system, or specifically the radio frequency heating system, like a microwave oven. This device generates power to heat plasma with high frequency and cold. And this is done by a device called a Gyatron. Japan is responsible for 8 units, which looks like this, because we completed production of 8 of them. We have gone through the performance test so as to make sure that it meets the required 1 megawatts. And the final shipment was made last week, and they actually arrived in the ITER organization last year. As Director General BARABASCHI mentioned, the radio frequency building is already completed, where they are to be placed. It is ready. And even though it's a little difficult to see because there's a cover on it, but power is supplied, and also the frame to put it in, and the manifold which provides water is now worked on. The celebration of the completion of the ITER toroidal field course. This was also reported by Mr. Baba. I would like to touch upon it again. The toroidal field course is the most important component. It is biggest 16.5 meters high and 9 meters wide. It is the world's largest superconducting coil. By the end of 2023, all 9 units that Japan was in charge was delivered to the ITER organization. And also Europe is in charge. And together we won the ITER award. And in July last year, because all the toroidal fuel codes were delivered, the ceremony was held. From Japan, as earlier I mentioned, that then Minister Mr. Moriyama took part. This became a precious opportunity to appeal the presence of Japan. And in the ceremony, the companies that make contributions to producing the toroidal code, Mitsubishi Heavy Industry, Arisawa Manufacturing, Manufacturing Electric Corporation, and Toshiba have been awarded the certificate.
60SA
And the next one is about JT60SA. JT60SA has been advanced version JT60, which is the world's largest superconductive tokamak systems. I said that ITER had 30 meters vertically and horizontally, and just as half as its size, 15.5 meters and 13.5 meters. And the plasma would be just half the size of that of ITER. And compared to other superconductive tokamak plasma, it is quite large. And before it start working, this would be the largest plasma that this can generate. It's been proceeded by Japan and Europe. We are now trying to realize fusion energy. And there are three purposes in doing so. The first one is to lead ITER by conducting construction, commissioning, and experiment, so that we can make use of the insight learned, so that we can lead ITER. The second one is, as mentioned earlier, to establish the method of regular operation of high-performance plasma necessary for a demo reactor. And the last one, which I think is the most important, that is to develop talent leading ITER and demo reactor development. These are the purposes of this plan. When the systems were completed in 2020, in 2023, we conducted the integrated commissioning. As a superconductive systems, it achieved the world highest d-diameter plasma, current 1.2 MA, as you can see in the photo. I said earlier that it would be the largest plasma until the ITER has been completed, but it generated the world's largest tokamak plasma with 160 cubic meters, which was awarded and certified as such last year. And the assembly of the systems and the methodology of testing the plasma operation, these pieces of information have been shared with ITER organization. So this is the unprecedented achievement we've achieved, which has been greatly appreciated by the ITER organization. As mentioned, we are seeing that this has been leading the ITER activity, as mentioned earlier. And JT60SA in this plan, we would like to start a plasma experiment on a full scale as soon as possible. That's one of the important things that we need to do with regard to fusion energy. And Europe, as there may be some different views and would like to need a persuasion, we need to convince the European countries or solve technical problems and issues. And from 2026, we'd like to start a full-scale heating experiment. And for that to be achieved, we are working on various activities inside, outside vacuum vessels. During integrated commissioning, the vessel was empty, but inside, a diverter and stabilizing plates have been installed. Should be installed, as well as heating systems needs to be further reinforced, and measurement devices should be added to the vessel. And this is about vacuum vessels related components. And plasma needs to be heated inside, and it should withstand the heat. Diverter, you can see the photo here, that needs to be installed at the bottom. And to stabilize plasma, you need to install stabilizing sheets as well as tiles for stabilization. There's some order in installing these components that needs to be done going forward, and ports needs to be installed, and it's now in progress. Before installing diverter, we need to install other components for controlling a plasma. And now we are installing these other components. And each component has its name. And there are some coil to correct a erroneous electromagnetic fields, 6 units multiplied by 3, 18 units that have been already installed. And high-speed plasma positioning in control coil. This is a very large coil to be installed at the top and the bottom. And this is the correction coil, so you can put it readily or from the latter phase, but this has a diameter of 8 meters, and it's not possible to install it later, so you need to consider the right order. From one port, you need to install this conductive materials, and on the platform inside the vacuum, we need to wind coil inside the vessel. And it hasn't been done in this scale of tokamak in the past, but we've been doing this. And ITER would require similar methodology, and they are very much interested in it, and we've already shared this information with them. What you can see in this photo at the top, you can see a high-speed plasma positioning coil. We've already wound them up. And this is heating system JT60SA. Is equipped with neutral beam heating system. Electrically, they are neutral, and high-speed fuel can be injected into the plasma for heating. To put it simply, when you pour hot water into the bath, you can increase the temperature of bath. That is an image. And as mentioned earlier, the radio frequency, as with microwave oven, you can apply radio frequency for heating. This is another system we are to use. And there are various neutral beam systems. It may be difficult to see here, but using these beams, we can inject beams from various directions into plasma using this system. And the reinforcement work we are doing now, we are going to add this brand new neutral beam systems, as well as a radio frequency heating system, which should be added up further. You can see at the bottom of the beam part, it's too high to lift up, so we need to put them in half and insert them one by one. You can see the photo of installation. And the radio frequency generating source is gyrotron, as with ITER, and gyrotron-related power sources are installed in this photo. Now, the lower unit of neutral beam, how it is installed. This is the video in fast-forward manner. You can see this weighs 50 tons. It's very heavy, and there's just a 10 centimeters space, and you need to achieve the accuracy of plus and minus 2 millimeters. It requires a great accuracy and technical capabilities. And now I'd like to show you what's going on in JT60SA inside. So Mr. Takahashi, the head of Tokamak System Technology Development, will give you some information from the ground. I think he hasn't received the cue. Good afternoon, everyone. I'm Takahashi, head of Tokamak System Technology Development. I'm now in the main room of JT60SA. Today, I'd like to show you JT60SA undergoing systems reinforcement. This is JT60SA. The height is 16 meters, the width is 13 meters. It is as the same size as the Great Buddha of Nara. The weight is about 2,600 tons. JT60SA achieved the first plasma in October 2023. And then we confirmed its plasma control performance, and it went through and completed integrated commissioning. Since January last year, we've started reinforcement work of the systems, and we are now halfway done. Today, actually, we are not working. It's working smoothly, and you can see operators working on the ground. Now, let us look inside. You can see something flashing inside, and this is the entrance to the vacuum vessel. When we go inside, then you can see some scenes in the photo. This is the cross-section of vacuum vessel. It is donut-shaped, and the height inside is 7 meters. The width is just half, 3.5 meters inside. And you can see a person here. You can see that it is very huge. Inside the vacuum vessel, it looks like this. There are 3-story scaffold inside so that we can install new components within the vessel. Outside, plasma heating systems are being installed. Let us take a look at that. I'm going to move a little. What you see below is the particle beam injection system. In the previous JT60U, we used this, and we will be reusing what we used. It's cylindrical with a height of 8 meters with a weight of 50 tons. You can see a box inside. There's a beam, a generating system to be installed inside this box. And as you saw in the previous video, we use a crane to install this container, and please take a look at how it's been installed. These particle beam injection systems are used to heat ions in plasma by clashing particle beams into ions. It causes heat. Depending on the conditions, you can heat electrons inside plasma. In JT60SA, for the next operation, we will be installing 8 units of this cylindrical systems. And this is where it is installed. To the left, you can see a stacked unit. There are 2. It is the same height as the entire system itself. To the right, you can see the 2 systems installed at the bottom. And there are only 10 centimeters or so in terms of space and interval with other systems, so you may crash during installation. We used a special tool in a very careful manner. And as a result, we were able to achieve the accuracy of ±2 millimeters. It is something like literally threading the needle, slitting the needle. And on the opposite side, there are 2 units already installed. Please have a look. JT60SA requires another heating system. That is a heating system using microwaves. The electrons in the plasma are heated by the system. Compared to beam injection, that heating by microwaves, it can be heat in the local area. JT60SA uses beam injection as well as microwave heating. With these, plasma will be heated. We came to the opposite side. I think the video had switched. Yes. From here, you can see the remaining 2 units stacked. We will be entering the latter half of the reinforcement work of the systems. Inside the vacuum vessel, one of the most important systems are diverter, as well as stabilizing systems of plasma, as well as the coil adjusting the position of plasma. These would be installed. Around this time next year, we are aiming to enter the preparation phase for the next operation. That concludes my explanation, but we always welcome your visit so that you can have a look at these systems with your own eyes. Now, this concludes the live stream from the JT60SA. Thank you very much. I'd like to hand it back to you. Mr. Takahashi, thank you very much for explanation. Yes, it is now in progress. And while we are seeing the reinforcement work, the research on the plasma has been in progress. And JT60SA studies have been continued by the JT60SA experiment team with experimental leaders from Japan and Europe and topical leaders. The team of 300 people was established in May 2024, and from Japan, the members will be joining from the core research plan. And the experiment team, they will be considering the planning of the work after the reinforcement as well as plasma scenario. That will be, this is the expectation of temperature and density distribution of plasma. And we confirm that we can generate a plasma with a temperature of more than 100 million degrees Celsius thanks to the heating capabilities reinforced. And also measurement devices and actuators, how we can maintain that needs to be also considered by the team, and the assessment of the research results have been confirmed. And we have been conducting lectures in the Japan Society Plasma Science and Nuclear Fusion Research, European Physical Society, and American Physical Society. And also we are giving lectures as well as submitting papers. And we are conducting various meetings and conferences in each area and domain. We are cooperating with each other to proceed with the research. Lastly, as mentioned earlier, I'd like to touch on a talent development, that is JT60SA International Fusion School, or GIFS. That's what we've been doing. And to develop talent who can engage in fusion energy for the future internationally, we invite 20 young researchers and students from Japan and Europe, teaching them physics and engineering, and giving them a lecture, combining lectures and actual exercises. It was well appreciated, and the second session was held in August to September last year, spending 2 weeks. Lectures and exercises were given to them, and for this fiscal year, thanks to the support by Naga City, we had an opportunity for cultural exchange. This person is a famous calligrapher, and under this person's leadership, Japanese and European students were able to enjoy the calligraphy, which they may not have much experience. This has been well regarded both by the students and lecturers. And in the opening ceremony, we received a message from former Mexican Minister Moriyama and EU Commissioner for Energy Simpson, and that was a great encouragement to the students and researchers. In the joint statement, we were asked to develop this activity further. So this time we've added some special practice and exercise session in domestic and European research institutions. We've conducted this in domestically, Rokkasho Institute, universities, and organizations. We went to these places and this is the photo when we visited Tsukuba University. And in March, we will be visiting Europe and ITER and ASDEX upgrade in Germany and JET in the UK to go through exercise. Following that, we would like to conduct the third GIFs this September, and practical sessions and lecture and exercises related to this program. What I've talked today, the ITER procurement and SA related activities, we have some posters and people who give an explanation, so please come to the poster venue where we can give you more detailed explanation. On top of that, on website and on social media, yes, we sent out some information. Please check them out as well. Thank you very much for your kind attention.
Thank you very much. Next, I would like to introduce the guest of honor, Mr. Masahiko Shibayama, the member of House of Representatives. Thank you very much for your attendance. Next presentation is from Mr. Kondo Keitaro, Group Leader, IFMIF Accelerator Group, Department of Fusion Reactor Material Research at Rokkasho Institute for Fusion Energy, QSD. And his presentation is titled The Next Challenge of the High Intensity Accelerator in the BA Activity, Superconducting Acceleration. Thank you very much for your introduction. I am Kondo from Rokkasho Institute for Fusion Energy QST. I'm the group leader of IFMIF Accelerator Group. And here I'd like to talk to you about the next challenge of the high-intensity accelerator in the BA activities. And this is what we are working on at our institute, development of high-intensity accelerator. And the picture that we are seeing is this. This is what we are building, high intensity, or this is the superconducting accelerator that we are putting together at our institute. And as it was already mentioned many times, and at fusion reactor, that we have the reactor core. This is where we cause fusion reaction of plasmas and then take out energy that's it produced. And through the fusion reaction, most of the energy comes out in the form of neutrons. And so neutron, we have blanket around a reactor core, and that's where the neutrons are captured and turn them into heat. So that's how fusion reactor works. And blanket and devices, there are many neutrons that hit those devices. And once neutrons hit the materials, those materials go through different changes. To be more precise, they become more fragile, they swell, or they may become radioactive. And once neutrons hit materials that we need to develop, we have been developing materials that can sustain neutron irradiation. And in the nuclear reactor, we study impact of neutrons irradiation. But in real situation, when irradiation continues for a long time, that to test that reaction, we need environment that is same as fusion reactor to gauge or assess the impact. And to perform the assessment, using accelerator, this the accelerator-driven neutron source. And IFMIF, what we call IFMIF. IFMIF is the accelerator-driven neutron source, and how it works is that you can see on this diagram, for deuterons, accelerate deuterons to up to 40 MeV, and then irradiate deuterons to liquid lithium, and that's how you create a very strong neutron field. And then irradiate materials in this field, and this neutral field is a very strong as demo reactor by irradiating to material, and you can test the impact or the after a long irradiation. But to build a system like this, we need a very good accelerator. To be more precise, as you can see on this page, we need 125 ampere of current. So this is the largest current that we would need, and we have to be able to operate at a constant speed. And for this institute, for this project, we are at our institute, we are developing IFMIF demo accelerator, accelerator. And for IFMIF, we take out low energy part. So that's this. And IFMIF, we accelerate to 40 MeV, and using demo accelerator, we accelerate to 9 mm, so it's not too big, but the 125 ampere and constant operation, those are the shared targets. And so we need a large current and large power for this accelerator. And with a large accelerator, current accelerator, beams can go different directions, but technologically speaking, low energy is more difficult. But if we can prove the beam acceleration with demo accelerator, I think this can give us a very good indicator or for building neutron field. And this is what we are working on at Lokasho Institute, Ifumihu Demo Accelerator. We call it LEPAC. LEPAC. This is the entire picture of LEPAC. And this accelerator is under the framework of BA. We are working with Europe to develop this accelerator. As you can see, Japan and Europe, many institutes are participating in this endeavor, and institutes, they develop their devices and equipment, and they get delivered to Rokasho, and then we put the pieces together as one accelerator, and test is performed by Japan and Europe. So this is a very unique international cooperation. And how accelerator is built is that there are 4 things, and we create deuteron, and then we use ISC to accelerate to 5 MeV, and next is superconducting accelerator to accelerate to 9 MeV, and once accelerated beam will be observed by beam dump. And using demo reactor or accelerator, what we are trying to achieve is that using very large current, a beam using very large current to be able to accelerate at a constant speed. So that's what we are trying to demonstrate. And the final target or goal at the constant or continuous operation, if we can achieve in terms of beam power, we can do more than 1 megawatt. And this is going to be an outrageously large accelerator. So this is a very big challenge for us. And next, this is the final, our final goal is 9 MeV and 125 MA and constant operation. This is very extremely difficult, and we have been testing accelerator in a phased approach. And the first phase, we have RFE accelerator, we install small beam dump and accelerate neutrons or deuterons to 5 MeV in a form of pulse. And you can see on this diagram, beam is produced in intermittently, and how much beam is being produced we call duty ratio. You use duty ratio in the first phase. It was 0.1%. That's so 1,000th. So 1 second, only 1,000th second that's where beam is being produced. And but the fastest in momentarily is 125 mA we tested, and we performed 2019. And as we planned, we demonstrated that we can accelerate at 125. And the second phase is to extend time that beam is being produced, and to that we need large beam dump to be able to manage a large power. And we built a beam transport line, a tentative beam line to be connected to our FK, and we started the testing 2021, and which I will explain later. The target duty was 10%, and last year, September, we were able to achieve 10%. And the final stage is this is where we install superconducting accelerator and accelerate to M9 MeV. And the final goal is to achieve continuous or constant generation, constant operation duty in the duty ratio is 100%, and beam power over 1 MW should be being generated in a constant manner. And we have to be able to manage beams. That would be a huge challenge for us to control beams. And before I talk about superconducting accelerator, I like to share the test result of the second phase. Test result, the second phase. Our target was 10% of duty ratio. The time that beam is being produced, we increase the time and to hit 10%. And the higher the duty is, the beam energy accelerator will be greater. If beam is lost in accelerator or beam hits somewhere, then it gets melted or damaged. The device or the accelerator can be radioactive. Therefore, beam loss has to be controlled so that how well we can control beam is very important to increase the duty ratio. And in our test, beam nature, or we assess the beam quality and compare to simulation. And if we see any differences, then we would change or improve simulation model, and we repeated that process. As a result of that, we are able to now predict beam movement at high precision, and we were able to improve the duty ratio eventually end of May last year at 120 ampere and 10% duty, or to be more precise, we were able to accelerate 8.75%. And average duty was, the average was 8.75%. This is a really great result. And the right bottom end is the table that plot RFQ on average, and you can see that LEPAC is by far the largest than the others. And for RFQ accelerator for neutron source, we demonstrated that it can work in a large current beam. So this gives us confidence to move on to the next phase. And now LEPAC, we are in the final phase, which is to test the superconducting accelerator. And we had a tentative accelerator to June, and this is being replaced by superconducting accelerator. And superconducting accelerator is in the final stage of being assembly at Rokkashosen. I like to show you how it's been put together, and superconducting accelerator to be installed in the beam line. That's what we are about to conduct. And I like to explain how this superconducting accelerator works. And it looks like a big box, and 6 meters in length. And this is a diagram. You can see what's in the box. And so there are so many different pieces or devices installed in the box. And the red circle is enlarged on the left-hand side. So there are major 3 pieces that the tube in the green is very important. This is what we call the cavity resonator. And this is made of niobium, which is a superconducting material. And within that superconducting accelerator, there are 8 cavity resonators. And that's how beams are accelerated gradually. And between cavities, we have superconducting magnetic solenoid coils. This is to keep beams together, and it gives convergence, a force of convergence to keep beams together. And cavities and solenoid are put together to generate acceleration and convergence in turn. And the beam, to accelerate beams, we use high frequency, and the beams need to be supplied into the cavity. So that's what we use coupler. Coupler plays as antenna to supply beams into the cavity. And this is the cross-sectional picture, and this is how it looks. And this is where our beams are accelerated in a cavity, and then solenoid converge them. And in the blue is where liquid helium will be filled. It's 4 Kelvin. It's minus 260 degrees to create a superconducting state. And this device, the box, the square box, it's insulating. It has an insulating property, and it's in the cavity. It's a vacuum, so it's like a thermos bottle, and that's how we achieve 4K or minus 26 degrees. And LEPAC, why do we test LEPAC? If we use LEPAC or superconducting accelerator, there are a lot of benefits. If we create superconducting state, there will be very less resistance, and we apply high frequency loss will be limited. And using that property, that we create high electric field, and also the heat will be reduced, and we can maintain that state for a long time. It's with this accelerator. In other words, what we need for a neutron source, and we can. This fit for our purpose to be able for us to achieve large current and constant operation. But there are some challenges to come with that. There are 3 challenges that are mentioned here. One of it is to create high electric field, and this is the acceleration part. And you can see that it's very complex system, and we need to make that very complex system using niobium, and we also need to keep that inside clean. And the second is to create a cryogenic state using liquid helium, and it has to be temperature needs to be reduced to 4K. And the third one is large current and constant operation, and the beam current is such, and therefore high frequency electricity is so huge as well. And to supply that heat in the cryogenic state, we have to make sure that heat does not get lost, and also we have to be able to control heat impact. So that's going to be key, and we have to make sure that beams are not lost. And the solenoid integrated accelerator is something we have to design, which is not going any easy feat. And how beams are accelerated, I like to show you a simple video. From RFQ, beams are injected into superconducting accelerator. Inside, you see vacuum. So there are 8 cavity resonators, and the particle travel through those cavity. They get accelerated, and as they travel through cavity resonators, they accelerate. Between the cavities, solenoids are placed to keep beams together, and we accelerate and converge, and convergence and accelerator take place in turn.
Now I would like to move on how we'll be able to assemble the superconducting accelerator. The tip is that we have to keep the cleanliness. And if there is some dust or any particles inside the cavity, then in the electric field, the environment will be degraded. So all the processes should be carried out in the clean room. And this is actually the clean room that has been established at Okasho, dedicated for this purpose. And before that, we'll have to undergo a special process, such as washing with auto pure water at auto high pressure. And at the same time, various other measures are taken to maintain a high vacuum inside and maintain to cleanliness. The photo on the left shows the connection process between the cavity and the coupler. And as to how the process is carried out, the cavities and solenoids are connected alternately. And this is done within the clean room. As shown on the photo, all the devices are aligned clearly, and all the processes was completed in the clean room. The next step is to integrate the equipment inside the insulated container that is cold to cryogenic temperatures. What you see in the photo is the insulation vessel. The cavity and solenoid is put outside, and after that, we make a minute adjustment of its positions, and after that, all the ancillaries will be installed. And for the cavity and the solenoid, we do the piping so that the liquid will go through. The liquid helium is connected. This completes the assembly of the parts, and then it is gradually inserted. Like this, we take some time to assemble the accelerator, and by going through this process, almost all the processes are completed. The next step is to move the superconducting accelerator, which weighs 12 tons. It's quite heavy. What we do is use what we call the air casters. We use the compressed air so that the foot or leg part will be moved slightly. What you'll be able to see in the bottom part is the air caster, just like a hovercraft. The compressed air is emitted and the accelerator is slightly levitated, which makes it possible to move the heavy accelerator. And so what we need to do before we move it into the building, the first step is to put it outside. And the photo here is the photo that we took about 2 weeks ago at Edokaso. At a building which is called the Joint Research Building. But we have to move the accelerator to the IFMIF EVADA Development and Testing Building, which is 100 meters, a few hundred meters away. And it is quite challenging to do all this work in a very cold season, but we have asked the local vendors to help us with this process. And we are planning to carry it to the building in late February. Then once it's delivered, we'll have to do the wiring and the helium piping, and it is expected to be completed within this fiscal year, and we plan to start the integration test in mid-2026. And the very first challenge that we have to do is the cooling test that cools the entire device. Concurrently with the assembly of the superconducting accelerator and the accelerator room, preparations for integrating the accelerator is underway. First, we have to remove what is actually installed at this point of time. And in order to keep the cleanliness, we have set up a temporary clean booth so that this process will be carried out in a clean environment. And then after that, this will be removed, and then the temporary booth will also be removed. And it is planned that the superconducting accelerator will be mounted in this area. This was the process in which how the superconducting accelerator will be assembled. And I think that you'll be able to understand how we have gone through this process, which is quite challenging. First, in order to create a high acceleration field, the cavity and other components were assembled while maintaining cleanliness. And also, in order to create the cryogenic temperatures necessary for superconductivity. Preparations for the heat insulation vessel is in progress. It is expected to complete within this year. So we first have to lower the temperature for this huge device, and this is the first challenge that we have overcome. And for the third point, there are many things that we have to overcome. The first thing we need to do is to evaluate the performance. And for the ultimate goal of high current and steady state operation, we need to proceed step by step by conducting beam acceleration tests so as to achieve technical targets one by one. So, in summary, at Rokkasho, a significant progress has been made in the development of a high-intensity accelerator for fusion reactor materials development. The demonstration test of IFMIF prototype accelerator LIPCA successfully operated about 10% duty ratio. And we are pumping our efforts to making the preparations are necessary for the integration testing at 2026. By realizing a neutron source from material testing, we will contribute to the demo project. Finally, the assembly of the superconducting accelerator at Rokkasho Institute have been supported by many Japanese companies who have cooperated with us. I'd like to take this opportunity to extend my gratitude. Thank you very much. Thank you very much. With this, we will like to complete a special lecture session. And the special lecture will start at 4:10. Please return to the hall by 4:10. Thank you very much.
Thank you for waiting. We'd like to start the latter part of the annual Symposium 2024 on ITER activities. We'd like to start a special lecture and I'd like to introduce Dr. Maeda Yuji giving us the special lecture today. Dr. Maeda joined NTT Telecommunication Networks Laboratories in 1991. He was engaged in research and development of solutions to social problems in the public sector, including natural disaster and emergency management, welfare, medical and healthcare, and cybersecurity. He received a PhD in Systems Information Science from Pietro University Hakodate, Hokkaido in 2013. He has been the vice president of the R&D Vision Group in the NTT Research and Development Planning Department since 2018, assumed his current position since 2020. He will be talking about the IOWN concept and NTT's challenges in space, environment, and energy to realize a resilient society. Dr. Maeda, the floor is yours. Thank you very much for introduction. Good afternoon, everyone. My name is Maeda, NTT Space, Environment, and Energy Laboratories. Congratulations on the annual Symposium 2024 on the ITER BA activities, and thank you very much for inviting me to give me this opportunity to talk about our activities and initiatives. As introduced, I'd like to talk about the IOWN concept and NTT's challenges in space, environment, energy to realize a resilient society, what we are engaged in. First, as introduction, I think you know about NTT, but I'd like to talk about NTT and NTT R&D. NTT Group has an employee of 340,000 people approximately globally, and we have group companies 67 companies, and about 40% of these companies are overseas based. And globally, NTT Data Inc. encompasses various global subsidiaries, but worldwide, ICT services and communication services are provided to our customers, so we've been expanding our scale. I belong to NTT R&D or laboratory. We have 2,300 researchers. We are located under the holding company as NTT R&D, and our budget for R&D comes from each business operating companies of NTT Group, and our outcomes will be put into businesses by these companies. This is the overall situation of NTT Laboratories. We have one center and 2 research institutes, and as you can see, we have these centers and institutes. And I belong to Musashino, the institute in Musashino City, Musashino Communications and Technologies Institute, engaged in network related, and that is where we have Space, Environment, Energy Laboratories are located. And it's been 4.5 years since the establishment of the institute. And from now on, I'd like to move to today's content. First, I'd like to talk about global environment issues, social environment issues. Every day we hear this a lot, and I'd like to briefly revisit these problems and issues and how can we solve these problems. I'd like to talk about these concepts from electronics to photonics, as well as even misfortune becomes blessing or adapting to environmental change. These are what I'd like to talk about in my presentation. First, global environment issues and climate change. I think you hear this kind of thing every day, carbon neutrality and climate change. As you're aware, due to climate changes, the abnormality in the climate has been occurring, and the linear heavy snow band have been frequently raised. We are seeing more and more severe natural disasters, and also water shortage, food shortage that have been rampant across the globe. The Japanese government announced and declared that we will achieve carbon neutrality in 2050. But CO2, carbon neutrality has been regarded as something innately negative. But in fact, the relationship between global warming and CO2, what do you think about this? Actually, this relationship between global warming and CO2 have not been proven. IPCC AR6. So this is the sixth assessment report, Climate Change 2021, and it is a report with a page of about 3,000 pages or so. Have you ever read this? It is very complicated, but regarded as something of the Bible, so that we are talking a lot about carbon neutrality. But then this report says that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. And this is what this report says. And there's no comment that CO2 has caused this. That is what I meant by it hasn't been proved academically, because CO2 hasn't been measured actually worldwide. 0.04% is the proportion of CO2 in the atmosphere. It is very difficult to measure CO2 itself, and also, as we are seeing extreme weather, typhoon, various linear rain bands, what do you think? What is the energy source from this? That is the vapor, water vapor over the ocean. This resulted in the various extreme weather, but water vapor over the ocean, this has not been well measured as well. Let us take a look at data. This shows the CO2 circulation on Earth. This IPCC document, regarded as a Bible, this is how we can understand the data. And this graph is not on the report. This is something we interpreted and prepared the drawing based on what is described in the report. And what you are worried about, CO2 emissions and coming from human activities and energy use. The CO2 emissions accounts for 4.9% of the total circulation of CO2, just about 5%. And what are the other sources? On land, for example, CO2 emissions from the land, including the living beings, 60.3%, and that is the case with ocean as well. 34% is the proportion from the emission, and absorption 35% or so. I said that these haven't been measured, but it has been measured to some extent, and these are the numbers we can see at the moment. So if we are trying to eliminate the emissions from human activities, that is not sufficient at all. CO2 emissions from the sea and the land and human activities, we need to take a circular approach to address all of these things. That is one problem I'd like to raise. And then where the CO2 emissions are measured. This comes from the website of the Meteorological Agency of Japan. You can see orange dot from the mainland Honshu area. You can see 4 points of CO2 measurement. They use very large equipment to measure CO2, and sometimes they use airplane and vessels. And you can see worldwide CO2 emissions are measured in this manner. And we use satellite as well for CO2 emissions, but as the resolution is quite small, you can identify some trend, but this is the data we can see every day in terms of GHG emissions. This is what it is. We are now working hard and not to burn fossil fuels, but this is how we measure CO2, and what we are targeting just accounts for less than 5% in terms of the GHG emissions across the globe. Turning to water vapor, which causes extreme weather. And this also comes from the website of Japan's Meteorological Agency. You can see red and blue dots, 16 dots on this map. In this map, we use what is called radio zondi for measurement. Twice per day, it measures the data to the ocean in the the far-off coast, we conduct the measurement of water vapor. You may assume that water vapor can be measured through satellites and others, but actually raindrops and clouds can be taken in image, but humidity or water vapor, they are too small to be measured by radar or satellites. That's not possible. On land, it's possible, but what I've been saying, the energy source of extreme weather, the water vapor on the ocean, this hasn't been measured at all. And the meteorological agency in the linear rainband region, they use vessels to go to East China Sea using a dozen of vessels, try to measure the data over the ocean, but that cannot cover everything. My point here is that as we don't have much perfect data, can we have confidence in the forecast of such extreme weathers? That is not what we can do at the moment without sufficient measurement. And I'd like to talk about energy. Climate change problem has been replaced with energy problem or challenges. I think many of you are aware of this. But as I've been saying, fossil fuel use reduction, that is, of course, in itself, and also we should use more and more or renewable energy instead of fossil fuels. However, our EVs are a true savior to this problem. In Europe, EVs lose its momentum, and in the US and the new Trump administration, they stopped the support for EVs. And also in Japan, we are trying to increase the number of solar power generation, offshore wind power generations, but hardware for such power generation comes from overseas countries, including China. Is this in Italy a good thing? Or, while at the same time we are seeing much continuous increase in the amount of information and energy consumption in our society, as you see a lot in the coverage by the media. The data center accounts for 2% of the worldwide energy consumption, and it's been on the increase. An entity accounts for 1% of the total Japan's power consumption, as we have data centers as well. And to what extent would it increase? This is the data. The amount of information on the web, on the internet, you can see it increases in an exponential manner. And energy and power consumption would also increase in an exponential manner. And this is about the data centers worldwide from 2018 to 2030. It is expected to be 13-fold. It will be a drastic increase in power consumption. And one of the factors are something we see a lot, that is generative AI. The spread of Gen AI accelerates demand for power. For example, GPT-3, a bit old, but GPT-3 need to consume a 1,300 megawatt hours, equivalent to 1 unit of nuclear power reactor. And it's been on the increase, and that is per learning, and that's me on the increase. And also, social environmental issues, as we are seeing every day, the division and pandemic, and Ukraine and Palestine issues, as well as change in power in various countries. In this regard, we are now reaching an inflection point, as all of you are already aware. And to put it into perspective, energy problem is the economic security problem, and to address to deal with the energy problem, we need to think about economy and say security. And for carbon neutrality, we should regard carbon neutrality from the perspective of new economic growth strategy. I've been saying a lot of things, but what should we do exactly, and what are the right things to do? That is something I'd like to talk to you today in my presentation. There's no definite right answer to these problems, then what should we do? I'd like to talk about what kind of solutions could be possible. Current technology is inadequate and innovation to break through limitation is needed. That is something we need. And NTT believes that one of the ideas to break through limitation is shift from electronics to photonics. That is what lead us to the IOWN concept, and also to let it become blessing. We need to adapt ourselves to environmental change. So I'd like to talk about our how we take on challenges in our institute. Of course, technology alone cannot solve everything. At the same time, we need to think about the new images of society as well as social systems. But in this presentation, I will just focus on technologies. Now, the IOWN concept from electronics and photonics. What we are trying to achieve is to have dramatically lower power consumption and ultra high-speed data processing. I'd like to show you a video first. Is it possible for this world to change? Is it possible to change this world? The future is the cumulative effect of the changes we make now. Take that first step toward the future. IOWN. IOWN will create a network and information communication platform that replaces the flow of all information with light in order to contribute to the resolving of social issues and create business. It is also characterized by its extreme innovative vision. IOWN will connect all information on people and things in aiming to realize a mutually happy and harmonious state for everything in the natural world. This is, in fact, an extremely difficult state to achieve. For example, the simultaneous implementing of multiple and diverse initiatives such as SDGs is possible when the goals are mutually compatible. But to save the global environment and goal to promote economic growth may lead to a conflict. We believe it's possible to achieve such goals at the same time and create new value. That's what IOWN is all about. Moving forward, the number of devices connected to the network will skyrocket around the world, dramatically increasing the burden on the network and boosting the consumption of power by individuals, companies, data centers, and so on. The global environment is expected to deteriorate due to increased supply and consumption of energy. In the modern world, economic growth is achieved through the massive consumption of energy. But is it possible to reduce energy consumption and achieve economic growth at the same time? To overcome this difficult issue, IOWN has achieved a breakthrough. One of the three factors that has enabled this is the old photonics network, which converts electronics with photonics to massively boost power efficiency and reduce electricity consumption to 100. Moreover, it will realize a dramatic increase in communication capacity and lower latency. Digital twin computing will also realize interactions that supersede simple simulations of the real world by allowing the free combining of a variety of digital twins of everything from people to things in cyberspace. It will enable predicting of the future. Cognitive foundation will allow the use of resources that extend beyond the domain of industries and regions through a multi-orchestrator capable of integrated management of a variety of resources. These technologies will reduce energy consumption while simultaneously allowing economic growth. They will also function as the basis for realizing a better sustainable world by creating many new services and solving social issues. This is not a dream, but steps have already been taken toward its realization. IOWN 1.0 will be launched in 2023. It will then evolve into IOWN 4.0 beyond 2030. Of course, realizing this will require collaboration with a wide range of partners as well as a variety of breakthroughs. IOWN Global Forum is an organization that aims to realize and promote IOWN. So let's listen to what the members hope to achieve.
Optical wireless networking are going to change the game completely.
And we do hope that we be part of the leading group adopting the service to be offered.
Numerous companies all over the world are now starting to support and take part in realizing this vision and technologies for IOWN, striving to realize a natural world in which everything is able to coexist in harmony. Thank you very much. How was that? IOWN, I'd like to give an explanation. Innovative Optical Wireless Network. This is the acronym IOWN. The keyword here is photonics technology, from electronics to photonics. Photonics, optical, has been used, the term used for the optical domain and telecommunications, for example. But in IOWN, these electronics and photonics are combined using the electronics photonics convergence. What it is and why we need to use photonics, that is electric wiring, that is a distance, the horizontal, that is the distance, and as we see the distances enlarges, the power consumption would be expanded, and the optical wiring, when you see the distance increases, there's no consumption increasing, and also with the longer distance, photonics will not suffer the increase of the power consumption, and also CPU will be heated within the electrical wiring, and the heat will be generated.
However, photonics wiring does not generate any heat, so that's why we focus on photonics. And this is the progress of improvement of optical technologies. At NTT, more than 60 years, we have been studying optical technologies. In 2019, April, optical transistor. For the very first time, we successfully developed optical transistor, and that we were able to reduce consumption by 94%. And then we developed all optical switches, optical logic gates, and those are the basic foundation or basic technologies for the IOWN concept. And IOWN 1.0. 2023, we already started the service, and this year, 2025, IOWN 2.0. This is a device for connecting board and applying photonics around chips. That's going to come into service, and from April 13th to October 13th. There's an Osaka Expo. At the Osaka Expo, using this new technology, computer servers will be displayed at our pavilion, and a new computer server, it's a low energy consumption, so that's 1/8 of the consumption. That's the energy needed, and this is the very first time we are going to showcase in the world, and I would encourage you to come to visit our pavilion and experience IOWN. And IOWN 3.0 2028 is the connecting chips using photonics, and also and then photonics applied in the chip. In 2030, for 2030, our goals are to low power consumption 100th, and high capacity, high quality, and low latency to 120 to 100th, as we show you in the video. But we cannot achieve this alone. We have an IOWN Global Forum. It's a consortium, and there were 155 organizations are the member of this forum as of December last year. If you are interested in participating in the forum, we are happy to welcome you to this forum. I am running out of time, but I'd like to explain what we are studying at our institute. And this is what we would like to achieve, vision of the society, and we would like to offset our negative impact, and also global change. We need to be resilient to the change of the global environment, And so environment burden zero, and generating new energy and observing capturing CO2, and also being able to measure environmental impact, so that we should be able to adapt to the new environment proactively. There are 3 things that I wanted to share, but I am running out of time, so I like to be a little bit go quicker. And the energy, next generation energy, and we have a fusion energy optimal operation. We have a panel exhibition, so I would encourage you to visit our panel exhibition. And first, future prediction of global environment. We mentioned that we do not measure water vapor, but actually we do. This is the current typhoon for a long time, and the transportation could be disrupted. It can have a huge impact. The impact is becoming ever greater if typhoon is not predicted. If we can predict a typhoon 3 days before where it's going to traverse, then we can minimize the impact on the societal system, and the people can manage what they should. People can control their behavior or what they should do, and to improve precision, we need more data and to unravel how the typhoon works, and we also need to be more raise the precision of simulation. The currently typhoon measurement, we use a remote sensing using satellite system, but our team that we directly collect data immediately related to typhoon instead of using satellite system, so that you can be more conducive in predicting typhoon. This is the actual footage that we are measuring in high waves 2022. We work with Okinawa Science Technology University in the center of typhoon category. We measured ocean and atmosphere, and we measured 9 meters high of waves. We were able to capture data that cannot be captured by a satellite system. However, immediately in that typhoon, but it is really difficult to capture data amidst of a typhoon, and to be able to measure typhoon in a very difficult situation. We are improving our technology, and based on the invaluable measurement data, we can study the mechanism, or we can unravel the mechanism of ocean and atmosphere, and we work with the other experts to be able to predict typhoon in a more precision manner. In the future, NOTT is propelling space and integrated network. We'll work with that network, and at the global level, a satellite IoT sensing is something we would like to achieve. And this study is not limited to typhoon, but the linear band, rain, current, and also ocean ecosystem. By collecting different pieces of data, we would like to better understand how the global environment works and the mechanism. We would like to be able to predict extreme weather, and to that end, using IoT sensing, we are hoping to collect data we have never collected before. So that's something we collect by satellite systems. So by collecting pieces of data we never collected, we would like to be more precise in making predictions. And the next one is lightning. It's something rather easy to predict. So this is also another our effort or endeavor to turn disaster into a blessing. The lightning is one of the natural phenomenon that can have a huge impact or damage on society. If power goes out, our life infrastructure or public infrastructure can be disrupted. So, and at NOTT Institute, we are studying technology to manage or control lightning. By lightning, this is to reduce damage but also using the huge power of lightning, we can use this to serve our purpose. And today, controlling lightning and also charging technology is something we are studying using multiple drones by IOWN, and we guide lightning, and so to protect city or critical infrastructure. And this is the inducing mechanism of lightning. First, use drone. We hoist a wire with weight, and then it gets discharged to the clouds. This is how we induce lightning to have guide or direct lightning onto the drone. And then using the energy being generated, we direct the energy to the system or institution that we can turn it into different forms of energy. And we're also studying how we can store such energy. This is the key here, is to be able to develop a drone that can sustain the power of lightning. Faraday cage is to protect the drone from a current or generated from a lightning. This project was born 2020, and after many trial and errors, as a result, the artificial lightning, that is 5 times bigger than the average lightning, we were able to develop drone that can sustain the power, and to test if this drone can sustain natural lightning, and we can direct energy. But it was very grueling, and it was more difficult than we expected in such a adverse weather. It was raining, snowing, and we have to make sure that the researchers are safe, and we can keep the environment safe. If this research come to fruition, not just a mobile lightning rod, and we can also use lightning energy as a renewable energy. Since I'm running out of time, I like to move forward. And this is a very dangerous study, but we are very serious about this. And we were able to develop drones, but now we were working on a technology to be able to predict in a more precise manner, and also turn lightning energy into something else. I wanted to share something else as well, but I have a video, but we don't have, since I don't have much time, I don't have time. And the CO2 conversion on the ocean and land or terrain, I mentioned that we need an approach to be able to capture CO2 in ocean, and we use algae using genome and re-engineering, and also using neutrons to cause mutation, and algae through changing algae to be able to photosynthesize twice as much, and then to capture or contain CO2 for a long time. So that's the study we are doing from algae, for large algae such as seaweed. And we have shifted our scope to include large algae, and through food chain. This is something we are planning to do to capture CO2, and also terrestrial animal. We do also re-engineer genome, but we use different cell, and as we capture more CO2 underground, but also by optimally circulate nitrogen, we can reduce the nitrogen to be generated and then capture more CO2. And this is also using the mechanism food chain. And next year, 2026, we should be able to achieve the carbon fix 1.5 times. I ran over my time, but change the world through innovation that exceed the limits. So that was one of the agenda I wanted to share, and the remaining agenda I have to rush through. Thank you very much for your attention.
Thank you very much, Mr. Maeda. Now we'd like to move to the technical sessions. To realize fusion energy early, we require broad participation from industry. Today, we've invited 6 companies contributing to ITER plan, MBA activities, as well as demo reactor development. We will hear presentations from 6 companies. First, we would like to invite Mr. Nogami Shuhei, Assistant General Manager, Engineering Department, and the Thermal Management Division, Light Material. Thank you very much for introduction.
My name is Nogami. I am from IINO Materials. And I would like first to congratulate you for holding today's symposium. And I am very pleased to have this opportunity to be able to give a presentation. Even though we are a material manufacturer, we are now getting involved in the fusion business. And so I would like to explain what we are doing. After we will give a brief introduction of our company, and then I would like to talk about what we do for the ITER diverter, and also about the advanced material, which we call the fusion grade advanced materials. Firstly, about our company, A.L.M.T. We have our head office in Tokyo. The number of employees is 2,600. The material that we deal with is tungsten and others, the rare materials. We are part of the Sumitomo Electrics and are involved in the industrial material segment. Again, it's a repetition, but the materials that we use is tungsten, diamonds, and molybdenum. I would say that it's not really visible in the product you will usually see. It's a sort of underpinning materials. However, and we are involved in electronics, semiconductors and telecommunications. We are making investments in this field. And one of them is ITER. And so that is why I am here today. And now moving on to ITER. Many of the earlier presenters have touched upon this, and we are involved in the diverter, which is one of the key components of ITER. A diverter neutralizes and discharges particles that flow into the plasma. That is what this device functions. In accordance to this, quite a high level of thermal power will be emitted. It is said that it's up to 20 million megawatts per square meter. So the key issue will be how we will be able to alleviate its impact. And because tungsten is used as a plasma-facing material, it is because it is a material that can be used under harsh environment. And even though diverters was initially thinking of using carbon, but depending on several conditions, they have changed the material to tungsten, and that gave us an opportunity to go into this business. This is what it looks like. The OVT is one of its components. It is not a single plate of tungsten. There are 3,300 tungsten monoblocks composing this part. The size is 30 meters, 30 meters by 10. And for OVT, it's 3,300, but because they are 58 units, we are supposed to manufacture 200,000 monoblocks. And we are now involved in manufacturing of tungsten monoblocks for the OVT, but we are the only company in Japan. This is because we are the only one in Japan that can produce in a fully integrated manner. And we can start from the power. We can make the adjustment from this level, even though there is a strong load from the heat. We are able to adapt. And we have gone through performance test, even though the original materials can be affected. But the so-called cracks will not appear in the case of our monoblocks. And the deformation is also controlled. Because we have been evaluated with this quality, the thermal load test conducted by the ITER organization had determined that our product is suitable enough for actual use. And then comes the questions of mass production. Maybe if it's 100 and 200 that they need, we'll be able to deliver a superior product manually. However, the volume that they need is 1,000 and hundreds of 1,000. And we have to ensure uniform quality and needs to be traceable in the case that any kind of faults would occur. This is the phonocone. For example, we applied 2D codes for traceability so that we will be able to get back to the point that has been manufactured. Automated test is another point. By taking these initiatives, we are now establishing a structure so that we'll be able to provide hundreds of thousands of monoblocks with a stable quality. As earlier explained, there was a press release last summer. The full-scale outer vertical target, the protocol mock-up has been completed. However, there was just the starting point because to maintaining stability, it was the biggest issue. So we have to keep on striving. As to the OVT, the ITER's diverter, the inner vertical target, this is procured by Europe. It is likely that the auto manufacturer will provide this, but we actually enter this market. This owes largely to the achievement that we made for outer vertical target. The DA for Europe is Fusion for Energy. And they are now working with a local manufacturer together with our company. Now, as to what will happen after ITER, we'll have to think of devices that will operate for a long period of time, which means that it is expected to irradiate neutron. Then it means that the issues that it did not involve in the case of ITER can erupt. We have to look at phenomena that will occur in low temperature, high temperature, as well as what would happen by neutral eradication. All these materials and information, characteristics intertwined, this can end up in the life cycle of the material that we provide. Fusion is not only the area that we are involved in, so we have various technologies to cope with different situations. So we are now developing, although the volume is not large, we are creating new materials. The minute bubbles are dispersed within this area, which created a superb material. Or thanks to the cooperation with research institutions and universities, and we could demonstrate that actually reduces the impact from neutron irradiation, which led us that our policy was not long, but we have to look at the future. We have to cope with the monoblocks, and for this reason, we are now manufacturing thick plates. I'm not going through each of the dimension, even though we are required with the level that's required in ITER. I believe they will be able to provide it. Our perspective is to keep the basic idea and make the material stable in terms of its structure, and also to maintain the qualities for a long period of time. And what we want to do is to keep on manufacturing these products, and if there is a need, to make adjustment so as to accommodate to their needs. I have been receiving many inquiries and been evaluated. This is the final slide. A.L.M.T provides solutions, not only products, to contribute to not only ITER, but subsequent future energy system. Because the materials has been produced based on a long history and expertise, we will continue to pursue this course. Thank you very much.
Mr. Nogami, thank you very much. Next, we'd like to invite Mr. Takahashi Kazuki, Advanced System Design and Engineering Department, Toshiba Energy Systems and Solutions. Mr. Takahashi, the floor is yours. Thank you for the introduction. My name is Takahashi, Toshiba Energy Systems. Today I'd like to talk about our achievements and contributions for fusion energy development. Today I'd like to first talk about our contributions to fusion energy development, and then as a technical topic I'd like to talk about development of breathing blanket, as I'm in charge of this, and I'd like to give you the summary. First, the contributions to fusion energy development. Our company has been continuously participating in fusion energy development domestically and worldwide from 1970s, including superconductive coils and heating systems, as well as power sources. We have a broad range of product records, and I'd like to talk about a recent example. The first one, as other speakers have touched on this, the ITER toroidal field coils. Toroidal field coil, or TF coil, one of the major components of the ITER. It is the world's largest superconductive coil to generate electromagnetic fields to contain fusion plasma. You can see the height is 16.5 meters, which is very huge. Again, this size, this require a very precise accuracy on the order millimeters. We developed a dedicated manufacturing equipment as well as manufacturing method. As you can see on the left side, the coil is the winding part in the structure. Based on this, we've created 4 coils as well as 6 structure. We've been in charge of the manufacturing of these items and completed. What you can see on the right, one is the completion photo of Unit 4, which was the final one we completed. The next one is the design of ITER blanket remote handling system. Blanket becomes radioactive based on fusion neutrons. As people cannot access close to the blanket, the maintenance and replacement needs to be conducted remotely through remote equipment. Based on our long-standing experience, as well as the vehicle manipulator development and the insight based on that, we've been engaged in development of remote maintenance system for the blanket. What you can see on the right side is what we are developing. It's a blanket remote maintenance system. During the maintenance period, inside the vacuum vessel, it will deploy a circular trajectory on which vehicle will be running, and the manipulator will replace the blanket. The radioactive environment, it should withstand such environment and also achieve the accuracy and precision required for that work, and it's now in progress. Next one is manufacturing vacuum vessel and stabilizing plate for JT60SA and on-site assembly. We made 10 vacuum vessel sectors, which is the 360 degrees equivalent. Physics, machinery, welding, electric work, we try to integrate all the capabilities we have to complete the production and assembly, on-site assembly of vacuum vessels and various components, including coils made in Japan and other countries. The first plasma was generated through by JT60SA, and people in our company were very delighted to see that happen. And also in the next item, plasma stabilizing plates to be installed in the vessel. We've been in charge of manufacturing this as well. You can see stabilizing plates which will be installed within the vessel. We've completed the world's largest tokamak systems manufacturing as well as assembly. Other equipment, LHD, and fusion equipment for universities. I've been talking about tokamak devices, but other than that, there are various field containment systems as well as related equipment. We have good track records on other items. The LHD for Fusion Science Institute, Tsukuba University, University of Tokyo, IOWN, Kyushu University, Quest. These are the plasma testing systems, as well as accessory equipment and apparatuses. We've been in charge of manufacturing these items. Next, I'd like to introduce a development topic, the technical development topic, and this is about breathing blanket. First, I'd like to talk about the breathing blanket and ITER test blanket module. Blanket is an important item to extract fusion energy and to multiply fusion tritium as well as shield neutrons. In ITER, a test blanket module should be installed to conduct the world's first blanket validation experiment. Within the blanket, a neutron multiplier are installed inside as well as fuel multiplicator, fuel breather, and the reaction between these would generate tritium, which function as a fuel in this process. In test blanket module, or TPM for short, will be installed together with shielding items as well as frame within the port. And cooling water system, tritium collection system, and neutron measurement system. These are the accessory systems, and all the blanket systems overall needs to be tested as one. To summarize, blanket is one of the important components to generate tritium, and the validation test will be conducted with the ITER. Design of the blanket is something I'd like to talk about next. There are various performances required for blanket, the multiplication views and the structural soundness, as well as a huge exhaustion capabilities. And in terms of multiplication of fuels, we can reduce fuel multiplicator or breeders. In terms of the structure, we can add the structures, or we can add coolants to improve the heat, reducing performance. But as there's a limitation in space within the blanket, this performance poses a trade-off relationship. Therefore, we need to strike a right balance in design to achieve required performances and characters. We propose cylindrical shape as well-balanced blanket structure. You can see the semi-spherical structure with a thin thickness of the, but ensuring durability, and it would be beneficial in terms of fuel multiplication. As it has become a small unit, we can have a better handling performance in manufacturing. To achieve higher performance, we've been proposing cylindrical shaped blankets. And this is the development of blanket system overall. For the validation testing at ITER, we are developing test blanket system TBS, including accessory systems, and the insight we gain through test blanket system development that can be also used for the development of demo reactor blanket. On the left side, this is the design of test blanket module and related photos and images. We conduct structural analysis as well as other analysis, as well as prototyping. In the analysis, as you can see on the left side, we conduct a finite factor analysis method that has been used to look into the temperature and structure. As you can see in the middle, sub-modules have been prototyped. Through this, we are checking the productivity and the easiness in analysis and testing. In terms of the auxiliary systems, the system design, control design, and related analyses and prototyping have been conducted. On the right side, you can see this is the prototype of tritium collection system, a hydrogen-absorbing alloy tank. In this manner, we've been contributing to the ITER test blanket system as well as demo reactor blanket. In summary, since 1970s, we've been continuously participating in development of fusion energy-related apparatuses and equipment. The latest result is the on-site assembly of JT60SA, which has been completed, as well as the completion of manufacturing of the ITER TF coil. We are now engaged in the ITER blanket remote maintenance system, as well as the development of test blanket system for ITER. And the development of blanket system, we are contributing to the development with the proposal of a cylindrical blanket, as well as auxiliary systems. The design, analysis, and the application of derived technology from superconductivity based on the long-standing technology we've accumulated, we'd like to help you all. We would like to further contribute to the development of fusion energy. Thank you very much.
Mr. Takahashi, thank you very much. Next presentation is from JGC Japan Corporation, Mr. Kuroda Yasuhiro from Nuclear Project Department, Industry Solution Division. Thank you for your introduction. I am Kuroda of JGC Japan Corporation, and thank you very much for this opportunity. So those are the topics that I'd like to present today. First, I'd like to briefly introduce our company. Our company is a corporate group with JGC Holdings Corporation as the holding company, and our headquarters is located in Yokohama. Founded in 1928, our company employee count and revenue are shown here. Our main segment is comprehensive engineering, and domestically we operate under JGC Japan Corporation, while internationally we operate through JGC Global Corporation. We provide various plant EPC services in the fields of energy transition, healthcare, life sciences, industrial city infrastructure, and resource recycling. Since the 1970s, we have expanded our business in the nuclear-related field, primarily focusing on nuclear fuel reprocessing radioactive waste treatment plant project. In the case of fusion and accelerators, we have leveraged our strengths in nuclear plant engineering to participate in various initiatives. Today, I'd like to introduce development of process, the performance of verification testing equipment, which have worked on the with QST, and the procurement of the ITER deterioration system in Tokai Tritium Process Laboratory. First, I'd like to briefly touch upon basic concept of ITER deterioration system prototype. The ITER tritium plant facilities are mainly composed of fuel processing facility and deterioration facility. The deterioration facility is responsible for removing tritium that has leaked into the building atmosphere, as well as removing tritium from the gas discharged by various systems in the fuel processing facility. And this system is a crucial for safety feature, preventing accident, and the construction of tokamak reactor is currently underway at the ITER site, and the implementation of the deterioration system is planned from around 2035, when the DD fusion experiments are expected to begin. Procurement responsibility is shared by Japan and ITER. And the ITER deterioration system, I will call ITER DS from now on, currently consists of an NDS system for normal operation and 6 SPDS system for emergency situations. Each module consists of catalytic combiner and a scrubber column, both normal standby operation. A maximum processing capacity is set as 1400 normal meter cubic hour. A normal DS is designed, and it's an analog control, and for standby we have on-off control approach. The deterioration mechanism works as follows. Gaseous tritium that permeated and leaks into the atmosphere is first introduced into the catalytic combiner under operating temperature of 200 degrees to 500 degrees. The tritium reacts with the oxidation catalyst, converting into a gas containing tritiated water vapor. This gas is then directed to the bottom of the scrubber column. Pure water is dripped from the top of the scrubber column, evenly wetting the surface of the packing material. As the tritiated water vapor in the gas interact with the water on the surface of the packing material, and traditionally, molecule sieve systems have been used to collect tritiated water vapor in the tritium handling facilities. However, for ITER, a risk of assessment of potential functional failure, such as equipment malfunctions, led to the adoption of scrubber method as a new technology. And now I will report on the background and result of the design and fabrication of the ITER DS qualification test rig. As for our involvement at TPL, in 2012, we designed and fabricated the first pilot at 20% scale scrubber column. Due to the innovative nature of the scrubber technology, it attracted attention from the French nuclear regulatory authorities, and from this time onward, qualification requirements for the performance of the DS system were imposed. In addition, the IO-JADA joint procurement arrangement was signed in 2014, with the final design and procurement activities for the actual equipment being led by IO and integrated performance testing being by JADA. Other word QST. As part of JADA support activities between 2016 and 2018, we conducted modifications to the existing pilot scrubber column and performed vibration testing. In 2021, we completed the final qualification test rig, a 2% scale integrated catalytic recombiner scrubber column test unit. I will now explain each of these projects in order. First, the initial pilot scrubber column. At this time, while scrubber columns were already widely used in many chemical plants, their ability to remove tritiated water vapor had not yet been demonstrated. Based on the process conditions that had successfully achieved DF1000 at the laboratory level, and considering the ACS processing capacity of the TPL building, we designed scrubber column at approximately 20%. Due to the dimensional constraint, the anticipated height was 11 meters, while the laboratory floor height was 6 meters. As a result of this height limitation, we decided to split the system into 2 units, but design them to function as one integrating column. After the equipment was handed over, QST carried out qualification testing demonstrating the removal performance of tritiated water vapor under the most conservative saturated steam conditions. Next, the modification of the scrubber column. In response to the French regulatory authorities' request for confirmation of the scrubber effectiveness, we upgraded existing scrubber column to allow observation of its behavior under conditions closer to actual operating condition, which was to so-called adiabatic, and specific modification, including installation of humidification column bypass line surrounding installation work was done. And after QST carried out qualification testing, obtaining accurate dynamic characteristic data under ITER, and ITER operational condition regarding the relationship between tritium decontamination factor and value, which is ratio of molar flow rate of water vapor, the molar flow, and this attributed to the establishment of operating conditions ensure both tritium removal performance at 99%. In 2017, we conducted the scrubber column seismic testing, which was another important verification item in the DS qualification process, and carried out modification to enable evaluation of deterioration performance before and after that. And this test was supported by Mitsubishi Heavy Industry. The process involved 1, installing the internal component into new scrubber column, 2, performing the seismic test under conditions that simulated seismic motions expected at site. Number 3, carefully transporting scrubber column to TPL by sea and land while ensuring minimum disturbance from external factors during transport. After the scrubber column was delivered to TPL, we carried out the installation work to replace the existing scrubber column with the vibration tested. And following the equipment handover, QST performed qualification testing, and it was confirmed that there was no significant decrease in the tritium decontamination factor of the vibration tested scrubber column compared to before that vibration. This demonstrated that tritium removal performance could be maintained. And finally, the integrated catalytic recombiner scrubber column testing. In response to the French regulatory request for confirmation of the effectiveness of the combined integrated system, we designed and fabricated the final performance verification test rig for DS qualification. Prior to this, IOWN had formulated over 30 normal and abnormal test scenarios by combining test gas properties and equipment operation plans based on the assumed profiles of ITER's normal operation and accident, including fires. The integrated test rig was designed and fabricated at approximately 2% scale of the full-size system, taking into account allowable process balance at the ACS connection point in the installation room to allow for the creation of various test gas scenarios. We equipped the unit with facilities for supplying steam and impurity gases. Additionally, we incorporated a control design feature of simulate both NDS analog control and SBDS. And after it was delivered, QST conducted qualification testing, confirming the test required deterioration rates are met over 99% during normal operation, and under fire we confirmed 90%. And this successfully completed the final performance verification for DS. And following this, IOWN joint procurement team began the procurement activities for the ITER-DS full-scale system, and in early last year, international tender notice for the final design of fabrication was issued by IO. Currently, our group is informing consortium to participate in the bid. That concludes my presentation on our effort towards the ITER-DS procurement. Recently, through our DS qualification activities with QST, we have been recognized for our achievement, and I am pleased to announce that our company's plaque was installed on the industry wall at the French ITER headquarters building. I would like to take this opportunity to express my sincere gratitude to everyone at QST for their long-standing support and guidance. We will continue to work together to contribute to the development of this field. Thank you very much for your attention.
Thank you very much, Mr. Kuroda. Next, from Hitachi, Senior Manager of Fusion Acceleration Department, Nuclear Business Development and Management at Center. Mr. Yasunori Koga will give the presentation. The floor is yours. I am Koga from Hitachi. Thank you very much for giving me this opportunity to address you all. I would like to give a presentation in Hitachi's contributions to fusion energy. This is the agenda that I will cover today. First, I would like to cover Hitachi's fusion and accelerator business and contribution achievements in ITER and BA activities in BI and neutral beam injectors. And I would like to cover these items in my report. First, our business in fusion and accelerators. On the left-hand side, there's a fusion, and the right-hand side, accelerator. The photo that you will be able to see are the devices from the 1970s. Based on the generators, we have been using electromagnets and also superconducting. We have combined these technologies so as to provide facilities related to these technologies to research institutions and universities based on their guidance. The technologies that we have acquired throughout the years, superconducting and high-level magnetic decision is now used in MRI as well as accelerators universities. It's also used in healthcare field, including medical particle radiation. And these technologies are further being developed in other organizations in our company. This shows you the recent initiatives for the fusion energy. ITER is shown here. And the demo reactor development that is related to the superconducting coil, which I will cover later on. For the accelerators, MGB2, which have been developed inside our company, we have used in CLIC and CERN. It is now being discussed whether to be adopted. The range of the temperature that it is operate is quite high. It's 25 Kelvin, and so it might be commercialized. Also for CERN, we are now developing the high radiation upgraded version of the linear collider. This is what we are working on currently. Now I would like to move on the contributions to ITER and the BA activities. First is the manufacturing of protective equipment of ITER and BTF. BTF is now constructed in Italy and Padua. It is the same size as ITER, which length is around 100 meters. It's a huge test facility. It is now going through the test. And during the test, the insulated transformer has been damaged. And this became the starting point for us to create additional protective equipment in order to enhance the reliability of the test facility itself. Because this is a facility that continues ground faults and short circuits, and because of this characteristic, we started to look into this possibility. There are two methods in order to cope with this. That is to improve the inside of the insulation structure. However, it is more reasonable to attach a new device externally. For this reason, we have inserted protective equipment in between the deck. The total length is 12.8 meters and FY 13 meters. And the volume is minus, the mass is 118 tons. And the L factor and the resistance is connected vertically. So it's held into this device, and the test has been completed. It's being transported. And next is the manufacturing of transformers for the ITER NBI. This is the tokamak at ITER, and currently at INER's NBI, there are two lines. Two lines are expected to be constructed. The NBI is minus 1 million volts, which requires a huge voltage. However, it is 10 units, minus 200 kilovolts by 5 stages, plus 2 lines, which makes a total 10 units. The biggest DCG among the 5, so we call it number 1. And this is the actual photo. The height is 7.7 meters, and the weight is 170 tons. And it's now being produced, started from DCG number 1. A different transformer that when I talked about MBT, we have the 2 transformers with the same specification, and we are now adding the protective device. We have started manufacturing from 2023, and the process is still ongoing. Among the other 10 MBIs at ITER, one of the issue is the absorption structure in the electric line. When an earthquake occurs, and if the Tokamak building will shake severely, the line connected, the relative of the displacement is going to be around plus minus 300 millimeters, which has become a serious issue. What makes the issues even difficult is the fact that it goes through the building, and inside the building, the object that moves with high voltage will go through, and this makes the issue even more difficult. As a measure to cope with this problem, as you can see from this slide, we are going to adapt horizontal bellows, and also the component of displacement of forming structure. By going through the anti-seismic analysis, we are now trying to deal with this product. The bellows that absorb the horizontal displacements, we have the intermediate pipes as well as the gimbals, and the size is 12 meters. By putting a slight tilt in this device, it can be a positive displacement. If it's moved by 300 millimeters, we have gone through the measurement of what will the expected change will be. And the result was almost the same as expected. And the data will be fed back to anti-seismic analysis, so that we will be able to come up with a better design of this device. Next is the ITER diverters. I'm sorry. It is the ITER diverters, which has been presented by several people. This is the subject to the highest thermal load in the vacuum vessel. So we are now working on the prototype. And this is what is assigned to Japan, the OTV, including the backup. We need 58 of them. In terms of structures, it is SSS, steel support structure, and PFU. These are the components. Regarding SSS, XM19, which is the thick-walled welded structure, is used, but it is not easy to be carried out in TMF. The blazing and bending process is quite difficult. Currently for SSS, as shown on the left-hand side, and they are in the cassette type, and also the blazing and bending process has completed. Next is JT60SA. In order to increase the power, all MBI systems have been reinstalled. The MBIs that had been used in the past is now reinstalled, and we are going through this work. The photo shows you a PNBI, which was shown in the video, as well as how it's connected on the ground. The size is quite extensive, and the work is now carrying out. And the third control coil, we have also produced 4 units of them, and it is now worked so that they can be installed. Now the efforts toward J demo. We are now in line with the action plan for the development of a prototype. This is the coil, the correction field coil. And we are prospecting that adjustment of 2 to 4 times can be realized. For the diverter, we are working with Tsukuma University, the pilot Gamma PDX. And we are now delivered a pair of superconducting coil. With one refrigerator, the coil that being cooled, this is one of the biggest devices that we have provided. We are now commencing research on the correction field coil. And by utilizing the expertise that we have acquired through the work that we have done, we want to expand it at the international level. Since the 1950s, we have been working on national project for fusion researcher accelerators. In recent years, we have participated in the ITER project for nuclear fusion development, and we are aiming to make contributions to achieving that target. We will continue to contribute to the early realization of fusion energy through technology development for prototype reactors and other projects. Thank you very much.
Thank you very much for your presentation, Mr. Koga. Next, we'd like to invite Mr. Baba Takashi, Acting Director, Fusion Engineering Office, Nuclear Energy System, Mitsubishi Heavy Industries. Mr. Baba, the floor is yours. Thank you for the introduction. My name is Baba, Mitsubishi Heavy Industries. Today I'd like to talk about the challenge to high heat flux component for ITER diverter. This is the outline of my presentation. How we've contributed to ITER project and B activity and MHI's activities until 2023. And I'd like to move into the main part, challenge to high heat flux component for ITER diverter, and I'd like to give you the summary in the last part of my presentation. We've been the major player in fusion energy since 1980s and participated in the ITER. With our monozukuri capabilities, we produced toroidal field coil, TF coil, diverter, as well as plasma heating systems and blankets from the stage of development and prototyping, so that we contributed to fusion energy power generation. What you can see in blue, these are what's in progress in the actual items, and what is in yellow is in the R&D phase. First, MHI's activities until 2023. Since 2019, we haven't made any presentations, so I'd like to talk about what kind of progress we've made. Since 2012, we've engaged in the production of toroidal field coil. I'd like to focus on key points. One of the characteristics is the size, 60.5 meters in height and 9 meters in width. And the weight is very heavy, but the accuracy is also rigorous. 0.2 millimeters is the tolerance you need to achieve. And MHI handled 5 out of 18 units. Involved in this linear part, we internally produced and supplied this to the final assembler. By 2018, in the final component, this is what we introduced in the annual symposium. And today, I'd like to talk about our progress since 2019. Since 2019, there's the integration and assembly work had started for TF coil. More than 100 tons of parts needs to be managed on a millimeter basis to assemble, and the super miller needs to be used to conduct a hyper-affine processing to complete what is required for ITER. In terms of the first one, in January 2020, we completed for the first time around the world, and in August, the Unit 5 was shipped in 2023. As the integration has been going on, what we shipped, the DF coil, has been regarded as subsector to be combined with the vacuum vessel. And what we delivered, the first one and the second one, they have been regarded as the first sector and installed to the pit. Later, the shielding plates for the vacuum required repair, and we went into this period, but that has been completed. Now we've restarted the assembly. Thus, we've been contributing to the progress in ITER. The major part of my presentation, challenge to high heat flux component for ITER or the diverter. This slide shows our R&Ds for plasma-facing components. In 1980s, we focused on materials and brazing, the technology required for that, not only for ITER, but JT60, we've engaged in diverter designing in that process as well. Based on that, we are developing the diverter for ITER. This is the outline of the ITER diverter. As been mentioned, so I'd like to skip some of these things. but there would be the circular and the install at the bottom of the vacuum vessel. It needs to withstand the high heat load and particle load. It needs to exhaust unnecessary impurities outside the vessel. It will be subject to the plasma impact directly, and heat impact would be something similar to 30 times as large as the space shuttle entering the atmosphere. So it should withstand this heat and damage and function. It requires a quite complicated structure as well as a sophisticated manufacturing technology. Divertor is composed of 4 parts or components. The OVT is what Japan offers or creates. This is the OVT detailed configuration of OVT, PFU and SSS, plasma facing unit and steel support structure, major components for this part. PFU, there are 22 PFUs per OVT. It would be the 22 units required, and per PFU there will be 150 the blocks required, and it needs to be installed to the coolant piping and brazing and bending, and through that tungsten blocks and the cooling piping requires a brazing and bending as key technologies required for PFU. Turning to SSS, it is not a simple structure and shape. It has a very complicated structure. And to provide a coolant to PFU, it is hollow inside. To create that structure, it needs to be uncreated in a separate manner, welded later. XM19 austenite-based materials would be used for SSS, and it requires the soft cutting and soft welding. Therefore, the welding quality needs to be ensured, RT inspection, as well as low distortion welding. That is what are required as key technologies for this SSS. By combining these, we can create OVT. And 11 PFU has been assembled, and then against the plasma surface, the required tolerance would be on the order of 0.1 millimeters. And also tungsten monoblocks, about 3,000 blocks are required, and you need to be mindful of the gaps and the stages on each of these monoblocks. In terms of quality assurance, it requires a very significant hard effort. It would be installed within the vacuum vessel, so leakage confirmation would be also necessary. Here, I'd like to briefly touch on our manufacturing technology for OVT. The first one is the joint welding technology between different materials of PFU cooling piping. We've adopted E-beam welding so that we can weld a copper alloy and an Ni-based alloy. And this one is about brazing based on the cooperation with a partner, based on the extension after heat application in the vacuum heat processing. We've optimized jigs and established the precise brazing technology. And between the gaps and spaces between tungsten blocks, we've realized 0.4 millimeters plus minus 0.1 millimeters in terms of the precision. The next one is called bending or PFU. It is raised in a straight manner, but that needs to be bent. And after bending, you need to achieve a very strict tolerance. To achieve this accuracy and tolerance, we've developed a high precision bending method. This brazing and cold bending, what are the troubles here is that you cannot do machining eventually. It should be this accuracy and tolerance needs to be achieved after bending. That is the difficult part with regard to this process. The last one is machining of SSS. The PFU on the top needs to be supported by SSS with high accuracy as well. Otherwise, you cannot achieve the requirements. So this the tolerance has been very strict on this. And where PFU are located, we came up with a unique manufacturing method through the coordination with ITER. Our proposal has been adopted and to be reflected in the prototype. Based on these activities, we've made 2 prototypes. What you can see on the left side is this is the PFU prototype. Through brazing, yes, this is what we confirmed. Brazing, the testing conditions are exactly the same as the actual operation of ITER. As this test, we passed this test. We received the permission to do the manufacturing of PFU for the actual ones. The right one is the OVT mock-up to scale. The accuracy and dimensions have been the same as what would be used for the actual ITER. And we completed these 2 prototypes. In March 2024, we completed this prototype, and last July, we delivered it, and acceptance test has been completed. At the moment, we engage in manufacturing for the actual ITER. This is the summary. Since 2012, we've engaged in the manufacturing of TF coil, 5 units. We've completed the production in 2023. And the second one, diverter OVT, we've completed 2 prototypes and started the production for the actual ITER. And plasma heating systems and blanket, we've been collaborating with the QST for further development. And all the technologies are made in Japan. We'd like to greatly contribute to the social deployment of fusion energy using domestic technology. Thank you very much.
Mr. Baba, thank you very much. Next presentation is by Mr. Hori Hiroyuki, Deputy Senior Manager, Radiation Monitoring Instrumentation Section, Nuclear Power Department of Mitsubishi Electric. Please come onto the stage. I am Hori from Mitsubishi Electric. Thank you very much for this opportunity. So I'd like to explain about our initiatives for fusion energy. First, do you know who we are? Air conditioner. We make conditioners and elevators. But when it comes to energy, we also do manufacturing in the field of fusion energy. But if you search fusion energy on our website, you don't get anything. So I would like you to learn more about what we do today. And we are located in Kobe, and we are surrounded by mountains and oceans. So that's what our selling point to students. On the right-hand side, I like to explain what we have been doing so far. And there are some initiatives that we have been doing for many, many years. But recently, JT60SA, solenoid SES and EF, and ETA toroidal field TF. And we have been, and so these are the main large superconducting coils that we produced. And what we are good at is that here, as you can see, high intensity forced cooling conductor. Using that conductor, we can produce with complex forms and shapes. We have a technology to do coiling complicated objects. So that's how we build up our technology. And the slide here is what we have already presented at the symposium in the past. On the top, it's JT60SA coiling machine for JT60SA. And the bottom, you may have already seen this, but this is the ETA TF coil turning table. And about this topic, about coiling, is very interesting. And I wish I had all the time to explain what coiling is. And once I start going, I cannot stop. So I need to skip that for today. And as I have been saying, ETA TF coil, coiling part, and the 60SA, CS, and EF. Those are the pictures of of them. And for CS and TF coiling part, that's 100 tons, and EF, and the outer diameter is 4 meters and 12 meters and about 30 tons. And as you can imagine from the size, and not only coiling machine, but in the process jigs and equipment and devices, it was a huge project to produce and design all those components and devices to make the conducting coil. And for today's presentation, JT60 enhancement construction started about a year ago, and the part we played is assembling components within a vacuum vessel. I like to explain the part we played, which was assembling components in a vacuum vessel, and also our contribution to demo reactor development, which we proposed, which was dual stage rectangular conductor. And I will call enhancement construction as Zoriki Koji, but next, components to be put together in a vacuum vessel. There are so many parts and devices to put together. It might be difficult for you to imagine what I'm talking about, but so on the outer part, cryostat and vacuum vessel, they're already being installed, and ports that connect those two pieces, we transport heavy object inside and then build them inside. And as you can see here, it's like putting a huge battleship. It's like constructing a huge battleship, and the challenging parts are, and so we are going to put parts together in a construction that's already been installed, and so it requires very meticulous work. And this is a testing or experiment transporting object. We don't have any equipment to transport components into vessels, vacuum vessel, and it's very limited space that we have to work, and there's not only so much space that we can put things, and how alignment and assembling each work it requires meticulous work and very challenging. And I like to focus on the green part. There are 18 parts. It's EFCC. I like to explain about EFCC, and that's the green part, and the blue part, that's FPPC. Those are the two parts that I like to highlight today. And for EFCC in 2020, we didn't have much. And EFCC itself, it's 1 meter to 3 meters, and it's a carved coil, and the output is about 1 ton. And as you can see on ports here, we install parts from the ports, and we also we need to install platform and put them on the walls, place the parts on the walls, the carved walls. And I wanted to ask you how you think we did it, but it's already answered here. It was already published in Twitter, KFCC. But anyway, I don't know if it's the optimal or the best solution what we did, but we came up with a desperate solution, and those are the solutions that we came up with, and there was required so much thinking. And 18 EFCC has already been installed. Next one is FPPC. And as KFC also mentioned, we have to do manufacturing in the vacuum vessels. Again, it's really large, and it's not like you can produce outside and then bring them inside. So within the vacuum vessel, we had to produce, needed to coiling machine and have insulating taping and heat curing and whatnot. We already needed those pieces, and so we need a heat resistance up to 220%, to 220, and this is what it's a picture that we recently took, and so we already see some more clear picture earlier presentation. And I like to change gears a little bit about demo reactor All Japan design team. We have been a member of design team since it was launched. And large superconducting coil, we had a track record, and we have been taking part in designing activities and putting forth proposals. And if we used a rectangular conductor, this corners, if it's become a dual curvature, we can prevent insulator being broken off. I think this is a very unique. I will skip the details here, but if you refer to papers or public paper, you can find more detail. And this is my last page. At Mitsubishi Electric, JT60SA CSEF coils, ITER TF coil productions has been something we have been part of. And today, JT60SA enhancement construction, and we are in charge of putting parts and components together in a vacuum vessel. So this is something we have been working really hard for the operation start service in 2026, and also demo reactor we have been participating, and we are willing to participate and give everything we have. But last but not least, as a maker alone, it's extremely difficult to maintain manufacturing capacity to be able to produce such a large equipment. But to keep our capability fresh, I would appreciate the project coming onto our way. Thank you very much.
Thank you very much, Mr. Hori. With this, we will end the technical report. Lastly, the Vice Chair of Organizing Committee of Annual Symposium 2024 on the IWA activities, Mr. Ejiri Akira will give the closing remarks. Thank you very much for attending today's symposium. Our symposium started in 2012, and we have reported almost every year on the results of the international project ITER and Japan-Europe project Broader Approach, BA, and activities of the companies that participated in the project. ITER, we can now see its shape, and for BA, the Local Fusion Institute has continued to achieve results, and in the year before last year, the JT60SA device at Naka began its operation. This achievement owes greatly to the contributions of many companies, researchers, and policymakers. I'd like to express my sincere gratitude. I believe that we were able to recognize this through today's symposium. Going forward, we may be facing many challenges that we need to overcome, and I would like to ask for your continued support and encouragement, as well as the support and guidance of the young researchers and students who are here today. Starting from this year and onward, the symposium will be hosted by QST. We would like to carry over the tradition built by the Fusion Energy Forum, who have been the organizer up to now, and we would like to make the symposium even more fruitful and expand it further. With this, I would like to bring the annual symposium to the close. Thank you very much for participating and watching online. Thank you very much, Dr. Ejiri. Thank you very much for taking part in the symposium for a long time. Please feel free to leave the hall. Thank you very much.